Hello, hello, hello. Hopefully this is working. Welcome to my latest live stream. My name's Simon Whiteley. I'm a system safety engineer and accident analysis specialist from the UK. Today I'm going to be continuing talking about the Boeing Starliner propulsion anomalies incident that occurred in 2024 and the investigation report. We're going to complete, hopefully today, complete that report. Final session, 31st live stream, and then once that's finished I will put together a case study and then I will send out an email and invite people to join me on a live workshop. And so if you're interested in joining a live workshop, I will just there we go, look at that, fantastic. You can use this QR code. That'll take you to the registration page where you can join the waiting list. I'll just put that up on screen so it's big enough and you've got a bit of time to snap that with your phone. In fact, actually, I will stick a link to it in the chat whilst I'm talking about it. So copy link address. Let's see if the chat works. There we go. Join the waiting list. Let's put it on YouTube as well. There we go. Got some people chatting from YouTube. Let's see if that message works. There we go. Hello. Hello from Maryland. How are you doing? It's good to see you. Thank you for joining me. If you'd like to share any of your experience, please comment below. Just be mindful, there is a bit of a delay between what comes out of your computer or your phone. And if you write to me, there's a bit of a delay in my response. But yes, if you want to join the live session, the free workshop, I'll just put this on the screen. Pardon me, if you visit my homepage, whiteley-safety.co.uk, this is the homepage. If you need some help, if you want to have a conversation, please press the button. It says, I need some help now. Send me a message, fill in the form, send me a message, and we'll set up a call, have a conversation, see how I can possibly help you. And likewise, if you want to join the waiting list for the free live workshop, because as I say, this will be the final live stream of this series. I will go off and do all of my magical work, and then I'll put together some slides and some control structures, and then I'll send an email out to the people on the waiting list, and then we'll get together and have a great time, I'm sure. And it is a free event. It is a free workshop. I'm not charging for it. So come along, bring your friends. Anyone who's interested in STAMP, STPA or CAST, to come along and ask as many questions as you like. Clearly, we're going to be talking about the Boeing Starliner case study, but if you want to bring along any other questions that you're happy to talk about in public, because it will be a public event, you're welcome to do that. So yeah, please join the waiting list. Click the link in the description below. Right, okay, so in terms of where we're going to get to today, I'll just do a quick overview of the investigation report. So let's make sure it's big enough on the screen. So this is the investigation report that was released by the NASA PIT team, so to speak. We started looking at it during April, and I've been working on it on and off since then. We've essentially got through most of the body of the report. So section 1, 2, 3, 4, and then 5, 6, 7, and 8. So that's the main body of the report. And then we started digging through the appendices. Now, the appendices also contains 2 other investigation reports. One done by the STAR team, which is a NASA team, and then the SDRT to do with the data, and that is also a NASA team. So those 2 reports were attached as an appendix, and that's what we've been going through in the last 4 or 5 live streams, and which we will complete today. So let's just zoom out and go down to the bottom. Where is it? There we go. Yeah, there we go. It's down this part here. There we go. So this is, I'll go to the table of contents for this one as well. So this is the Starliner Tests and Anomalies Review, STAR, Investigation Team Report. And the table of contents is here. So there's various sections we've been to in the previous live streams, and we've got to essentially the last part, which is the Starliner Data Review Team Report. So we're going to go through that today. It's not particularly very long. Then there is the STAR Senior Review Panel, so we'll go through that. And then we'll go through some of the appendices that are relevant. And as I say, if you do have any questions or comments, or you want to share some experience, please stick it in the chat and I will do my best to get to it. There we go. Let's make sure the audio is working. Seems to be working. There we go. I can never be sure. I'm always paranoid that I'm on mute or something like that, or it's disconnected. But there we go. Right, let's get stuck into it. Excuse my French. There we go. Right. Yeah, we got up to that bit last time, so let's just steal one of these and put it over there. This is the jigsaw piece that I use a lot. There we go. So the Starliner Data Team Review Team Report, so the SDRT report. So this part of the report is essentially blacked out, redacted, and this is the SDR team members. So I completely understand why they would black out who the team members are. One of the things I would kind of comment on is it would have been nice to know what the roles are, or what part of the organization they worked in, or what experience they've got that is relevant to this investigation. But I can appreciate maybe it's quite a small distinct team, so if they say what they do, then people are going to know who they are. But as I say, from a sharing knowledge and experience for the general population and for the safety engineering community, it would have been nice just to have a feel to understand what the scope, what the context and scope of their experience is. There are 1, 2, 3, 4, 5 bullet points, so presumably it's a small 5-person team. And then here we go. Here is the scope. So let's make sure it's big enough on the screen for you. There we go. Right. So the SDRT. So this is the Starliner Data Review Team report. So let's just put a nice line across there. Starliner Data Review Team report. So there we go. Right. So the scope. The Starliner Data Review Team. In fact, actually, I'm probably going to forget that acronym in 2 minutes, so I will write it down. Hopefully I'll remember it better. Starliner Data Review Team, SDRT. There we go. There we go. Right then, here we go. So the SDRT, Starliner Data Review Team, focused primarily on the service module reaction control system thruster failures. And you'll recall from the previous live stream, I did point to a few controllers that are not really discussed in the previous part of the report that were previously redacted, but there was actually a repeat section in the report that contained an unredacted label. And this emphasizes thruster failures. But the question I have is, well, what about the control structure? What about the other controllers and their behaviors? Whether they're failures or not is irrelevant, really. It's just what is the contribution from these other controllers in the control structure. So focusing on thruster failures is really only part of the issue. Okay, so they focused primarily on the reaction control system thruster failures and reviewed available data for this failure across the orbital flight test number 1, number 2, and the crewed flight test missions. The primary goal of this sub-team was to look for data or opportunities where issues with the thrusters might have been uncovered in previous missions. Okay, that's really interesting. The team was interested in fault tree analysis, in the fault tree analysis process used in all missions, pardon me, specifically as insight to help determine if the current CFT fault tree analysis is robust and has reached the true root cause of CFT anomalies. I mean, based on what I've read from this report so far, I am not convinced at all. In fact, I would probably go so far as to say that the fault tree analysis is inadequate, but that's not necessarily the fault tree analysis fault. It's the type of analysis that they're using, and I would strongly suggest that they use STPA to really understand the issues here. Of course, I'm going to say that because that's the whole point of this, live stream, to help people understand how STPA CAST and STAMP could help them. But of course, if I was involved in this, as if I was invited to be involved, I would recommend doing an STPA, building a control structure, looking for the scenarios that contributed to this particular event, and then cross-check those with the fault tree analysis. And given the quality of the fault tree analyses in this report, being able to read them has been very difficult. Being able to see the actual fault tree analysis, I'm absolutely certain we could find some significant gaps in it. Having done that myself on previous projects and programs, different systems myself. So trying to determine if the current fault tree analysis is robust or not, I don't think is the right exam question, because it's not going to be, because it's a fault tree analysis. And that's no disrespect to the people doing the work. It's just the nature of the tool, the nature of the method. Anyway, I've laboured that point. Here we go. In addition to reviewing data, the team interviewed 8 technical experts, fantastic, covering propulsion, operations, and thermal disciplines. Right, so there's 8 technical experts. Brilliant. Right, so let's keep going. OFT1 mission. So this was the 12th of the 20th month. If anyone can tell me what month that is in the chat, that would be most appreciated. So the 20th of December 2019 to the 22nd of December 2019. Okay. So during the OFT1 mission, the mission elapsed time, which was supposed to be latched to L0 launch, was incorrectly latched in place at L102353, an error in the coding. That's interesting. So that's the first time that I mean, earlier on in the report, it does mention mission elapsed time issues, but it doesn't say specifically what they were or how they might have contributed or not to this particular situation. But given my experience on other similar systems, there is a possibility that issues with mission elapsed time contributed to issues with propulsion control. I'm not saying that happened in this specific situation, but there are potential scenarios that might contribute to it, of which haven't been discussed earlier in this report. Maybe over the next few pages that will be discussed. But like I said on the previous live stream and the couple before, this investigation did leave me a little bit cold as to whether they've actually dug far enough. And of course, they haven't used STAMP, STPA, or CAST, and you know, again, if you were to use those methods, you could dig so much more deeply. Yeah, I'll come back to the mission elapsed time stuff in a minute as we keep going through this. This led to the Starliner believing that it was over 10 hours into the mission at launch. Right, okay, so that is very interesting. Okay, let me dig my little jigsaw piece out. And if you've been watching these live streams since the beginning, this should be burnt into your brain by now. And if it's not, let's have a go at burning into your brain today. So this, if you're not familiar with it, is a very, very basic control loop. And it's based on the principles of control theory, if you're familiar with what that is. And essentially what this represents is a system or a situation where you have a controller, a stakeholder, a decision maker, that is in control of, either directly or indirectly, of some type of controlled process. And so if we were talking about the spacecraft and its trajectory, you know, the use of the thrusters to change its orientation, its trajectory, we would say that that is the physical control process of the spacecraft. Now, of course, if we abstract the spacecraft and look inside at the architecture of it, we're going to have some kind of thrust or propulsion control system of some description that will control which thrusters fire, when they fire, and for how long they fire. And of course, that will receive inputs from other controllers, such as human beings touching the controls, maybe even from other control inputs that have been pre-programmed by ground control or have been uploaded after the spacecraft has launched. And essentially what this model, this loop, this jigsaw piece represents is that relationship between the controller and its control process. And so for this controller to have any kind of influence over the control process, it needs to provide what we call control actions. And of course, to be able to provide control actions, the controller needs to make some decisions. It needs to decide what control actions to provide and when. Now, more formally, we might refer to that as a control algorithm. And of course, the more complex the controller is, the more complex the control process is, and the more complex the types of control actions it can provide, the more complex, by logical extension, that these control algorithms could be. Now, of course, the decisions, these control algorithms are based on what we would call process models, or if we want to be a bit more abstract, we could say they are the beliefs of the controller. And these beliefs, these process models, are based on primarily feedback from the control process. So if you imagine driving your car down the motorway, down the highway, and you see a vehicle in front of you, you know, your control process, you're monitoring the space in front of your vehicle. If you see that there's an obstruction in your path, then that will update your mental model, your beliefs, and hopefully you will decide that you need to press the brake. You need to provide a control action to slow your vehicle down before you potentially collide with an object. Now, of course, if you don't detect that object because it's dark and the object is dark and it's unlit, and you're driving at a certain speed and your headlights, you know, the distance that your light extends in front of your vehicle, it is possible that you won't be able to stop in time. You won't be able to press the brake, or you won't know to press the brake because you don't know there is an obstruction in front of you. And so, of course, your beliefs, your process models are absolutely fundamental to your decision making, and most importantly, whether you will provide a safe or unsafe control action. And so in this case here, this is talking about, hang on a second, there we go. In this case here, it's talking about during this mission, the mission elapsed time, which is essentially a process model about how much time has elapsed. And that mission elapsed time will be embedded within most of the controllers on the spacecraft, not necessarily just associated with propulsion control, but other mission-related controllers. Pardon me. And so if the controller believes that its current time is different to the real time, it may decide to provide some control actions that it believes are perfectly fine, and so there isn't a failure, it's doing what it's designed to do, but because it's providing those control actions at a different time than they might be expected, there's a real possibility that they could be unsafe control actions that lead to, potentially a near miss at best, or potentially a catastrophic loss at worst. And this little statement here, it says an error in the coding. So when we're talking about software errors in the coding, we have to then expand our view of the system, the control structure, and ask a question. Who or what is the controller of this controller? Who or what is higher up in the safety control structure hierarchy that actually does the coding, does the design, does the test of the algorithms for this controller that controls the trajectory of the spacecraft? And of course, using STAMP, thinking about things through the lens of a control structure, it can help you uncover the control structure so you can ask those kind of questions. Well, logically someone, a human, has been doing some coding. So why is it the code that they provided to be installed on the spacecraft was potentially unsafe? What were the issues going on there? Because these are not incompetent people. These are very, very well educated, very experienced people doing very, very difficult, tough work. So how could that happen? How could code that has an error find its way onto a real spacecraft carrying people? What is it about that whole control structure, from people typing code and using code generators and testers, all the way through to loading on the spacecraft and testing it on the spacecraft? What is the structure that's involved in all of that? And so the other part I want to emphasize is this bit. This led to the Starliner spacecraft believing, so, if this is the Starliner spacecraft and this is its trajectory or its propulsion system, if it believes that it was over 10 hours into the mission launch, when actually it was much earlier than that, how does that affect the decisions it's making? How does that affect the control actions? And how many of those control actions could be unsafe or have contributed to this particular situation? Now, of course, we're talking about the context of OFT1, so this was before there was any crew on board. But of course, if you're having these kind of issues on your first flight test, then what is the control and feedback structure to identify that there are issues, diagnose what is going on, and actually fix them before the next flight? What does that feedback loop look like? How many different stakeholders are involved in that? Okay, so following spacecraft separation from the Atlas V launch vehicle, so again, that is a potential candidate for inclusion in our control structure, Starliner is programmed to execute maneuvers tied to the mission timer. There we go. So that programmed to execute maneuvers, that is this control algorithm, that is the decision making, and that is based on a belief, a process model, which is the mission timer. So if that timer is wrong, for whatever reason, it doesn't matter the reason really. If it's not what it's supposed to be, if it doesn't match reality, then this controller will execute maneuvers tied to that mission timer. So you could argue, and we could have this conversation on the workshop, click on the link and register or on the waiting list. But is that strictly a failure? Is that really a failure of the controller? If it's providing control actions at the wrong time, is that really a failure of the controller? Not really. It's doing what it's supposed to do. If it believes that it's supposed to be making those decisions and providing those control actions at that point in time based on the mission elapsed time, that's not really that controller's fault, is it? It's not really failed. So, we need to look deeper than just focusing on failures and fault trees. Anyway, let's keep going. Right, with the incorrect... I hope that makes sense. Please give me some comments in the chat. Give me some abuse in the chat if you think contrary to that. Right, here we go. So with the incorrect time set, the Starliner attempted to perform incorrect maneuvers. There we go. So they are our, unsafe control actions. I mean, there is a bit. Let me just go on a bit of a loop from this point. Some people say, well, conceptually, what is an unsafe control action? And when we're talking about real systems working in the real world that have near misses or accidents, is it really appropriate to call them unsafe control actions? Well, when we're doing an analysis before we build the thing or before we send the thing operational, we would do an STPA hazard analysis and we would identify all of these unsafe control actions, candidate unsafe control actions. And these are essentially control actions that, with a specific context, will lead to a loss, will lead to an accident. And so we label those control actions unsafe control actions. Now, if we are doing an accident investigation or a post-event investigation and looking back through time with the benefit of hindsight, we would refer to those unsafe control actions as contributory control actions. And there's a few important reasons for that, but the main one is when we're doing an investigation post-event, we are blessed with the benefit of hindsight. And so when we look at a controller and the control actions it's provided and the context within which it was provided, we can see with the benefit of hindsight that the outcome is obviously going to be unsafe. But the controller at the time may not have been able to foresee that, may not have known that, and in fact might have been following its design, following its procedures. And so it's doing what it's supposed to do. And of course, if it doesn't do what it's supposed to do, then that could be dangerous. So we would refer to those as contributory control actions. And really, when I'm talking about this particular case study, I should be referring to unsafe control actions as contributory control actions. But functionally, they are exactly the same thing, just viewed from a different perspective in time. So incorrect maneuvers, again, incorrect in respect to what? What is the context? Is it with respect to the intent of the designer? Oh, this controller is supposed to do maneuvers at this point in time. That it has done it at a different point in time means that the label for those maneuvers is that they are incorrect. But we would refer to them as contributory control actions. These incorrect maneuvers led to excessive firing of the service module reaction control system thrusters, but importantly, no orbital maneuvering and attitude control firings. And these excessive firing was well outside of the qualified usage duty cycle, total pulse count, and total firing time. I mean, so that's about as bad as it gets. That's by the sound of its description. It basically provided lots and lots of firing of the reaction control system thrusters, and those firings were well outside the qualified usage duty cycle, total pulse count, and total firing time. So that's bad. That's really bad. As the STAR team noted, pardon me. This led to excessive propellant usage and 10 thruster failures. So all of these outcomes, all of these issues, because the controller decided it would provide some control actions. And it believed that it was the right thing to do in the right context, and it was not. That was not a failure. I suppose you could get into the argument about, well, Simon, is it not a failure on the part of the designer to not use STPA as part of the design? Well, it's a bit of an academic question, really. When this was designed was over 10 years before this thing was launched to fly. And so those issues have existed in the design for basically 10 years, or that's the impression I got from the early parts of the investigation report. So is it a failure on the part of the designers to use STPA to anticipate those issues? I don't think that's a really helpful, question or topic, because I'm sure they would use the methods and the tools that they think are appropriate. And STPA was not particularly that popular 10 years ago, so or in this context. Anyway, so 10 thruster failures, 9 of which were attributed to high pressure sensor temperatures. So if we're talking about feedback, everybody, here's the feedback path that tells the controller, updates the controller's process models, the beliefs, so that it can influence its decision making and the control actions it provides. If we've got issues with high pressure sensor temperatures, and one which was attributed to high solenoid temperature. Yeah, so there was issues with the sensors, the feedback that contributed to the thruster failures. Because again, it doesn't say here yet, and it might explain this later on, but when it says thruster failures, I think that label refers to a set of distinct failures. One is the actual thrusters themselves have had some mechanical issues, or it is to do with the control of those thrusters. And so if we have a thrust control system of some description, and its control actions are to turn valves and switches and everything else so that there is a thrust created. If the controller decides, oh, we're not going to use these thrusters anymore because we believe that there's a fault with the thruster, that means the thruster has failed, but it's not because the thruster has physically failed. It's because the controller in charge of those thrusters has made a decision that they're not going to use those thrusters anymore. So it could be a thruster failure, or it could be a controller decision, not necessarily a failure. This is the point I'm trying to make, and I'm probably labouring it too much. But when we're talking about safety through the lens of STAMP, STPA or CAST, we're not just focusing on failures. We're looking at, the system behaving as designed, and if it does so in a certain context, it is at that point that we have a dangerous situation. And this is what sets STAMP, STPA and CAST aside from fault trees and failure modes and effects analysis, because they specifically focus on failures and they don't necessarily cover situations where the system has behaved as designed. I think I've laboured that enough, so I'm going to keep going. Right, so we've got some findings then. Let's just move down. So the findings. The Boeing NASA teams did not consider the 10 failures experienced on the crew flight test to be thruster failure. Oh, there we go. So that's interesting. So did not consider the 10 failures to be thruster failures. They attributed to the issue of overuse and pressure transducer and solenoid failures due to overheating. If anything, the team gained confidence in the robustness of the thrusters because they continued to work even though significantly stressed outside expected usage. Boeing noted in a program control board presentation, orbital flight test mission elapsed time anomaly demonstrated robustness of RCS thruster design despite long duration of excessive usage. And then that's the reference there that it refers to, which is a report of some description. And that was July 2020. So that was written before the CFT flight. This smoking gun of the MET, mission elapsed time anomaly, was immediately adopted as the only issue. Okay, so let's just look at that for a second. So if this controller represents the investigators, and their belief is that the smoking gun of the MET anomaly they've adopted that as the only issue. So they believe the MET anomaly is the only issue. How would that affect their decision making? How would that affect their actions? Especially if they've not diagnosed it properly because they don't have adequate feedback, for example. Because of this conclusion that the thrusters were used incorrectly, the fault tree developed was not extensive or robust. Okay. So there was a decision there to use fault trees and to develop them to a level of maturity, which may have seemed perfectly reasonable at the time based on the belief that the MET anomaly is the only anomaly. It consisted of 3 legs with 21 total failure modes and submodes. Figure 102. Okay, so this redacted figure is the OFT1 Service Module Reaction Control System Thruster Faults tree, which is obviously helpfully redacted, which I understand why it is. At the completion of OFT1, so orbital flight test number 1, additional thruster testing was proposed, but not pursued. Okay, again, so let's have a think about it through the lens of this this control loop. So who or what is the controller that is making this proposal to do additional thruster testing? So if whoever that is, they've provided a control action that says, we propose doing additional thruster testing. And then whoever they sent that to, why didn't they do that? Why wasn't it pursued? Why did they not do that additional thruster testing? Why would it make sense? Team members went as far as preparing a draft test case, a draft test request for the NASA White Sands test facility. However, based on interviews with the experts involved at the time, the testing was dropped because it was believed there was no need to test thrusters in a usage profile like OFT1 actual usage, as this was not representative and known to be well outside of qualification limits. There we go. So, you know, the decision, as you can see, not to do it is based on some beliefs. And those beliefs in the context may have been perfectly valid and appropriate. But with the benefit of hindsight, that looks a bit dodgy. The teams noted that the high duty cycle usage of the thrusters was potentially damaging. Post-orbital flight test, team has been sensitized to SMRCS jet high pulse usage events. And again, excuse me, that's another email reference. There we go. And then we've got some redacted notes at the bottom. Not sure where they fit in. It says number 39, but I can't see the... Oh, there we go. That's 39 is there. And it refers to this reference at the bottom, which we can't see because it's redacted. Fantastic. Okay, right. So, however, no changes. No changes in service module reaction control system usage were adopted. There were some changes made to the orbital maneuvering and attitude control usage during the deorbit burn, but not service module reaction control system. Again, this issue was attributed to MET anomaly overuse. Solenoid and pressure transducer failures could have potentially masked poppet swelling issues. However, the rapid thruster recovery of OFT1 leads most technical experts to conclude poppet swell did not occur, or at least was not limiting the thruster performance. Okay, so again, you know, if we use our little feedback loop, we can sort of examine and understand where these issues might be considered. So we're saying solenoid and pressure transducer failures could have potentially masked poppet swelling issues, so that's down here. However, the rapid thruster recovery, so that's feedback, apparent rapid thruster recovery, led to technical experts to conclude poppet swell did not occur, or at least was not limiting thrust performance. So that belief, that decision, has then influenced their forward follow-on actions. Okay, so now we've got some recommendations and some lessons learned. So let's just zoom in a little bit. In fact, I'll just check the chat. Bear with me a second. Sorry, Crystal, I missed your comment from a few moments ago. But wouldn't it have been behaving as it was programmed if it was set at the wrong time? Oh, right. So we were talking about the mission elapsed time stuff earlier on. Where is it? Yeah, this bit. So we were talking about mission elapsed time. So, but wouldn't it have been behaving as it was programmed if it was set at the wrong time? I think from what you've written, I get the impression the question is more about the behavior of the controller and its relationship to mission elapsed time. Let me just bring that up on screen again if I can. There we go. So, but wouldn't it have been behaving as it was programmed if it was set at the wrong time? Yeah, so the controller will behave based on the control algorithm, the decision making, the scripts, the training, whatever. If this is a human controller, if they've done some training and they're doing some drills and they're the skills that they've got, they will follow those, those instructions, those skills, those decisions based on their beliefs. And if their beliefs are incorrect, for whatever reason, they will reliably do, the unsafe thing. And they might not even realize they're doing it. And so something like the provision of mission elapsed time, that controller needs to have its own time to monitor, but it also needs some kind of function in the architecture to ensure that time is synchronized across all of the controllers. So if you go into an air traffic control center, typically they'll have a really big clock that everyone can see, but they'll also have their own clock on their own workstation. And of course, in theory, those two times should never be different. But again, it depends on the architecture of the systems, the networks, the software, and everything else that displays those times. So having your own mechanical watch that doesn't get automatically updated is probably a good idea, because then you've got local control of your time and you can be confident that it's working. And if you really want to be safe, you could have two or one on each wrist. Anyway, I'm being a bit facetious, but I hope that sort of makes sense. But let's continue on this bit about recommendations. So, a recommendation is to examine the fault tree analysis performed by Boeing and determine if it is detailed and robust, and that blocks are used using objective evidence and not merely statements that are presented as factual without supporting data. Yeah, okay, fantastic. But that's not enough, as I've already said. It's not going to be enough, certainly not for this type of design with software and everything else. You really need to do an STPA hazard analysis, and I could absolutely help you with that. I could get you the results within a matter of hours, and then you could compare that with the fault tree analysis performed by Boeing or anybody else. I'm happy to put my money where my mouth is and do a comparison and show you how many different things you could find with STPA over and above fault tree analysis, and also much faster. I'm not suggesting that a beginner doing STPA could do it as fast as I could do it with my experience, but I could certainly find a lot of these issues very, very quickly. And I don't believe the fault tree analysis, even if you did the best fault tree analysis in the world, I don't think it would pick up these particular issues, because it's not designed. The tool is not designed to find these kind of issues. It will find the failures, hopefully, if the team have got a good team of people and they've got enough time and resources. But the non-failure issues you just won't find with a fault tree. They won't fit, especially where there is feedback loops and sequencing to some of these issues, knock-on effects. Okay, and determine it. Yeah. There we go. So the recommendation would be to do STPA. There you go. Do STPA. Pardon me. Where it is? Plus do STPA, and then compare. What we just done. And compare it with fault tree analysis. Lessons learned. Fault tree analysis can be compromised by the team finding a smoking gun. That is quickly determined to be root cause. Yeah, I agree with that. But that's just humans doing human things, you know, target fixation and all that kind of stuff. That is quickly determined to be the root cause. It is human nature to focus on the obvious. Yeah, absolutely. At the expense of other potential issues, requiring full and objective evidence that has been reviewed by independent technical experts for any fault tree block closure is critical. Yes, I agree with that, but it's the fundamental issue here is not just that. It is using fault tree analysis to look for failures and ignoring the what I call dangerous successors. You know, the controller has behaved as designed. You know, it's believed that the time was 10 hours more than it should have been, and so it acted based on those hours. That's a fundamental design issue. That's not just due to a failure. There are questions, I would argue, there are questions over the design, the control architecture of that thrust control system. I mean, we've not seen any detail of that, so I can't say for certain. But I'm quietly confident, based on experience I've had with other systems with similar issues, that you could look at that architecture and find some significant gaps in it. And I would be honoured to help and support, find those issues, get those issues dealt with. While the root cause of the OFT failures, there we go. Oh, there's a root cause, everybody. The only root cause, if I'm being really facetious, is that the control structure is inadequate, and that is why this loss occurred. You know, the reason that the control structure is inadequate is what the investigation should go and find out. And there are many reasons. There are issues with the design, the control architecture, the sensory feedback, necessary sensory feedback, issues with design, issues with investigations, issues with using fault trees. There are issues all over the place. Anyway, while the root cause of the OFT1 failures is likely tied to the MET, mission elapsed time anomaly, this mission presented an opportunity to identify a weakness of the service module reaction control system thrusters, that they are susceptible to failure. It's not just a failure. It's not just failures, everybody. Due to overheating, teams should consider extending learning from the actual failures to be more generic along the lines of, what does this show us? And are we sure the system does not have a weakness previously identified? I think the answer to that question is yes, it does have a weakness, and fault trees are not going to help you find them and fix them. You need STPA. Let's move on. Let's keep going. Right, so OFT2 mission. So this is the second orbital flight test. And this was conducted in the 19th month of 2022 and the 25th month of 2022. So the service module propulsion system uses fault detection, isolation and recovery scheme, where it checks for thruster chamber pressure as an indicator of thruster status. Any chamber pressure less than 110 pounds per square inch absolute is considered off or degraded. Any pressure above this limit and the thruster is considered to be on. The integrated, here we go everybody, this is the detail we want. The integrated propulsion controller, IPC, and the flight management computer use these measurements to determine if the thruster is on, and when it has been commanded off, thruster failed on, or off when commanded on, thruster failed off. For the OFT2 mission, the persistence or the number of failed thruster flags required for the flight management computer to remove a thruster from the availability table was set to 2. This means that the integrated propulsion controller had to detect low chamber pressure readings and set the failed off flag twice for the FMC flight management computer to read on the data bus. And I've just realised I've been talking on mute for a little while because, of course, I have. Yes, we've lost sound. Thanks, Crystal. Thanks for that. Well, let me. Could I rewind it and find out where it went quiet? That is a bit frustrating. I don't know if I can. Stand by. Let me just check if I can find out when it went quiet. Stand by. So 10 minutes. I'll do that last bit again because it's important. Because what I'm doing is I'm explaining how you would go from some textual information to an actual starting point for doing an STPA analysis. So I'm just going to do that again very quickly. So for orbital flight tests mission number 2 in May 2022, I essentially highlighted this section where the surface module propulsion system uses a fault detection, isolation and recovery scheme where it checks for the thruster chamber pressure as an indicator of thruster status. Any chamber pressure less than 110 pounds per square inch absolute is considered off or degraded by FDIR. Any pressure above this limit and the thruster is considered to be on. The integrated propulsion controller, and I'll just highlight this as a candidate for inclusion in our control structure, and the flight management computer uses these measurements to determine if the thruster is on and or on when it has been commanded off, thruster failed on, or off when commanded on, thruster failed off. For the OFT2 mission, the persistence or the number of failed thruster flags required for the FMC to remove a thruster from the availability table was set to 2. So if there's 2 failed flags, thruster flags, then the FMC, the flight management computer, will remove that thruster from the availability table, i.e. it will stop the spacecraft from using that thruster going forwards. This means that the IPC had to detect low chamber pressure readings and set the failed off flag twice for the FMC to read on the data bus. So thinking about what the control structure looks like, what I did is I highlighted the integrated propulsion controller and the flight management computer. I know that they are 2 candidates to be treated as controllers in the control structure. And the way that this is described, this part here, so the IPC and the flight management computer, the FMC, they both use these thruster chamber pressure feedback to determine if the thruster is on or is off, and the persistence of that. Hang on. The number of failed thruster flags required for the FMC to remove a thruster was set to 2. So the FMC has the ability to remove a thruster. So if we just remove thruster from the availability table. There we go. So that is a control. Let's duplicate the loop. So we've got 2 of these now. Pardon me, because I think it sounds like. There we go. Let's just do that. Send it to the back. It sounds like the IPC is this controller, and the FMC is this controller. That's what it sounds like, and it sounds like the integrated propulsion controller removes the thruster, whichever one has failed, from the availability table. And by extension, the availability table is a type of process model of the flight management computer. Maybe it's the other way around, actually. Hang on a second. So there's a process model of the availability table. There is also a process model of thruster status, but that thruster status also exists inside the integrated propulsion controller. The FDIR recovery scheme is a type of decision making, so that's in there. Maybe I could squash this up and stick it in somehow. There we go. I'll squash that in there. There we go. So let's just read that again then. So the IPC and the FMC use these measurements to determine if the thruster is on when it has been commanded off. So there's commands on, command off. Thruster command on and then command off. Excuse me. There we go. So there's those control actions. And then it says there, thruster failed on or thruster failed off. So these are, there we go, thruster failed on or thruster failed off. So they are the two assumed. There is a third state, actually. And often this is missed from control loop design. Unknown. Unknowable. So thruster state. In fact, actually, I should probably do it like this, shouldn't I? So it's all in the same box. So thruster state, failed off, failed on. No, hang on a minute. It's also thruster on, thruster off. Thruster on, thruster off, failed on, failed off, unknown. So there's the thruster states. Then we've got thruster chamber pressure. There we go. Let's look at that again. So we've got IPC and the FMC uses these measurements to determine if the thruster is on when it is being commanded off. So commanded off, thruster. It's not thruster, is it? It's thruster. In fact, I'll combine those two together. Thruster command on, off, thruster. There we go. There we go. So thruster command on, off, thruster state. There we go. Right. So they use these measurements. So the feedback they get is chamber pressure. So there's an important question here that's implicit from the description. I know there's not a technical architecture diagram in there, and I'm essentially building the control structure from a natural language report. So of course, if there's text missing that I don't know about, I can't know about, the model I create is going to be limited, if not flawed. Of course, if I had access to the real data, I could build a proper control structure. But the point I'm going to make architecturally is this. If the flight management computer has feedback from the thruster chamber pressure, that'll be in the form of chamber pressure less than or above 110 psia, and it determines that means it's off or degraded or it's on. Now there is an algorithm involved in that, so it's, with this pressure decide this is what the state means. And so you could have issues with the sensory feedback, you could have issues with the decision making. There's a lot of detail we could drill into, but we don't have necessarily the correct detail to be able to do that today. But the point I just want to make is the feedback that it receives might be directly from the thruster chamber pressure. So the arrow goes like this. No, that's not what I meant. Let me do that differently. Stand by. Let me do that differently. So right, so let's just assume for a minute there's a feedback path that goes from the control process, the thruster chamber pressure, directly to the IPC at the top, and that there is also another one, an equivalent one, that goes to the flight management computer itself. So let's just, in fact, what I'll do is I'll make it a bit easier to see, because at the moment it's a bit difficult, isn't it? Excuse my French. And it's this level. There we go. So let's, I don't know. Yeah, my diagram's getting a bit more complicated than I was anticipating, but what I'm trying to say is, if you imagine the feedback between the bottom layer, this layer, and this layer, it might be direct feedback straight from the thruster chamber pressure right up into the flight management computer, and it's just literally chamber pressure. Or it may be that this feedback path is actually sensors putting data onto a data bus, and then that data finding its way via the data bus to the flight management computer. And then also, it might be that it flows its way to the integrated propulsion controller via the data bus. Or it could be hierarchically, as I've presented here. It could be that the data is passed to the flight management computer, and either the flight management computer passes it completely unchanged, or it passes feedback which is representative. So it might literally be, that between this level and this level, that it is, the chamber pressure is whatever number it is. But when it's passed between this level and this level, it is just that the thruster is on, off, or degraded, and that's the message. So we'd need more information. We'd need to talk to the designers, get the design information out and have a look at it to understand which of those it is. Is it direct feedback, as in this one, or is it and this one, or is it in two levels? So I'll just put this one above and I'll show you what I mean. Is it like that? Is it in two stages? Because depending on which of those it is, if it's a direct feedback to the other control, they both have both direct feeds, then that's arguably a better design. But if there is a intermediary in the middle, that not only increases complexity, but it also increases the number and types of causal scenarios that lead to these issues with thruster, the beliefs around thruster status and availability. Does that make sense? Is there anyone in the chat who wants to give me some abuse about that? There we go. Right, I think sound should be coming through. So Yeah, come on. Is that working? Just bear with me. Well, it seems to be working. Yeah, I can hear click, so it should be working. So let's go back down here and have another look. So use these measurements to determine if the thruster is on when it has been commanded off. So who does the commanding on? Again, for the control path, the feedback path, there's a similar sort of question. So let's just move it over this side and change the direction of the arrows. So this one, and this one. Swap. Is that going to work? No. Can I only do it one at a time? Yes, of course, one at a time. That's helpful. There we go. So this is the feedback path and this is the control path. So these thruster on commands, are they only coming from this controller, or do they also come from this controller above? You know, where do they come from? And what happens if you get one controller saying thruster on and the other one saying thruster off? What's going to happen then? So yeah, that's interesting. But there we go. So it says the persistence or the number of failed thruster flags required for the FMC to remove a thruster from the availability table was set to 2. Yeah, so it sounds like the IPC is this controller and the FMC is the top controller. And it sounds like the FMC removes a thruster from the availability table. So that's a control there, control action. Remove thruster from the availability table. There we go. So that's the availability table there. They both have thruster status by the look of it. Failed thruster flags. Failed off flag twice. So this also does a failed off flag. Sorry, yeah, let me... There we go. So there is a failed off flag state in there as well. And it's flag set, no flag and unknown. And it says it's a mention there of the data bus. So there is a data bus in there somewhere. So the question is, where's the data bus? How does that fit into this? Is there a bus controller? Do any of these controllers control the bus? You know, is there a potential for it to cut itself off or cause itself problems being able to communicate data? I wouldn't be surprised. There we go. Right. So that's, I think we've done that bit to death, I think. So let's keep moving. There are a variety of data rates in use throughout Boeing. blankety blank. For example, the blankety blank, whatever that is. One major issue that has been identified and persisted through crewed flight test is that the propulsion system data is only sent via telemetry to the ground. Right, so let's just stick those in the control structure. So we're going to have the ground. And there will be some telemetry. Telemetry. There we go. So that's feedback to the ground. That's telemetry. And it's at a particular sample rate. So of course, if this feedback loop is not, the speed of this data rate is not representative of the physical, the physics of the situation, that can lead to all manner of issues with the control loop. And again, that's not necessarily due to a failure. That's due to the design and behavior of the data links. This can make it difficult to understand exactly how the blankety blank pressure are performing. In addition, the count of flags set comes through telemetry at blankety blank. 3 thrusters failed during the mission by exceeding the FDIR persistence limit. In analysing the actual data rates and pressure data sampling, the teams concluded that the thrusters were being shut down by the FDIR that was missing chamber pressure measurements. Right, so it said here, this bit, it said that both IPC and FMC use the measurements, chamber pressure measurements, to determine if the thruster is on when it is commanded off, so thruster failed on, or off when commanded on, thruster failed off. So which is it? So it was shut down by FDIR. So the FDIR is shutting the thrusters down. So this bit here, this is the thing that's shutting the thrusters down. It's not a very good colour on the eyes, that, is it? There we go. Fault. In fact, actually, Simon, why don't you just put a red border? Oh, you can't put a red border around it. Because, of course, you can't. I'll make it pink. There we go. So the FDIR is setting the failed off flag to set. So it's failed. So the thruster command is set to off. Is that right? Is that what it's saying? So the FDIR is shutting them down because it was missing chamber pressure measurements. So if we go up here, assuming that missing, because again, we don't know what the chamber pressure, how it's designed, how it specifies it. Is it literally just below 110, it assumes it's off? So if there's no pressure, is that treated as 0? Does that mean it's failed off? And if so, it sets the flag that it's failed off, communicates that around the control structure, and so those thrusters are lost, not because there's something wrong with them, but because there are issues in the feedback path or the beliefs of these controllers. I mean, we're getting quite deep now into the design of those control loops, and I'm not sure we're going to have enough information in the later sections of this report to actually understand this. But I'm hoping you can see how far and detailed we could go when we need to. So yeah, it sounds like the FDIR is doing its job. It's doing as it's supposed to. It's doing as it's designed. But it sounds like the control loop is inadequate. There's something wrong with that part of the feedback loop. But again, I would recommend we look into this in more detail. Okay, let's keep going. Pardon me. Findings. False FDIR fail-off occurred. There we go. So that's it. That's the unsafe control action. It's this here to do with FDIR. Occurred due to blankety blank settings. So there's some settings. Whatever that blankety blank is, the FDIR captures false low chamber pressure readings and counts as strikes. The blankety blank required to remove the thruster from the usage table. The thrusters recovered quickly, and effects of seat separation were expected to be permanent and weren't considered due to the service module thruster recovery. Seat swelling was considered as a failure mode. And as the STAR team has already noted, a Boeing presentation had a slide where the first bullet stated seat swelling was considered, reducing propellant flow, but since flow is controlled by trim orifice and injector, seat swell contribution to resistance change would be negligible. So trim orifice and injector. Can't remember how to spell. Where is it? Trim orifice. Orifice. And injector. Okay, so they are parts of the control path. So we can mention those. Seat swell contribution to resistance change will be negligible. When this presentation went to the next management briefing, excuse me, that bullet had been removed from the slide. Interesting. The experts interviewed by SDRT did not recall that a specific bullet, didn't recall that specific bullet and could not explain why it had been removed. Okay, so there's a question there over documentation control and configuration control. And for a document discussing safety critical issues such as this, the way those documents are updated and changed and controlled should be, auditable, traceable. So we should understand who and why that was changed, unless they're not controlling their analysis documents and presentations with much control for that config control. FDIR was identified as a root cause of the thruster shutdown. Okay, again, the concept of root cause is just nonsense. It is a contributory control action, yes. You could argue that's a type of causal scenario or a contributor to a causal scenario, but a root cause is a bit of a silly thing to refer to it as. It is a contributor. There are other elements in this control structure that clearly contributed to this. It's not just FDIR. Yes, there are questions over it, but there are bigger questions over, well, why is the FDIR even designed like that in the first place? If it's doing its job, which it is, it's supposed to do that, it's not a failure, then why was it designed that way? Why was the control structure designed the way it was? With apparently inadequate feedback paths. Why was that? Like OFT1, this became the smoking gun for the OFT2 mission, while the OFT2 fault tree was more robust than OFT1 with 5 legs and 83 failure modes and submodes. Once again, many fault tree blocks close without rigorous objective data. It's not, you could have all the objective data in the universe. Fault tree analysis is fundamentally not enough for these type of complex systems. That is the answer. That is the root cause, if you want to be facetious. Okay, right, let's have a look. Are we making good progress? What time is it? 19:29. So we've got... Well, we've... I'm thinking maybe we're going to need another live stream. I was a bit ambitious when I said 31 would be the last one. Anyway, let's... yeah, we need to keep going though. That's the thing. I need to get this done. Let's keep going to the end of this section, the largest section. And then we'll have a break. And then I'll continue, I think. So let's keep... So yeah, let's think about this. So this smoking gun thing then. Let's just draw a big circle around this. So this smoking gun here is about the FDIR. And then the smoking gun here is about... where is it? The MET anomaly. MET. And again, I'll just make a point here. The mission elapsed time stuff is... Where is it? I'm moving too fast, aren't I? So mission elapsed time is just one process model of one or more of these controllers. I imagine that this controller also has mission elapsed time. And so on the OFT1, the mission elapsed time has contributed to unsafe control actions, contributory control actions. And then on OFT2, we've got issues with the chamber pressure and the FDIR. And that's contributed to it shutting down. And in both instances, they're not failures. They are due to the way the thing is designed, apparently. So like OFT1, this became the smoking gun for the OFT2 mission, while the OFT2 fault tree was more robust. Yes, fault tree is just not good enough. It's just not good enough. Okay, so here's the fault tree. You can't read it. I can't really tell what it says apart from BMRC3F failure during OFT2 mission. Don't know. But looking at the size of these blocks and the depths of this, it doesn't look very deep. But again, it's a fault tree. It's not enough to deal with this kind of complexity. Several presentations make the statement that should this type of failure be seen again, the solution is to disable FDIR because the thrusters are fine. Like OFT1, these failures were not considered thruster failures, but were considered misapplication of FDIR. Right, there we go. If in OFT2, it is not possible to assign the root cause, but poppet seat swelling cannot be ruled out as a cause of the failure. Recommendations. The recommendations coming from OFT2 are like those listed above for OFT1. Focus on ensuring the fault tree analysis and evidence provided are robust and objective. It's not enough. The fault tree analysis is simply not enough. Lessons learned. Fault tree analysis can be compromised by the team finding a smoking gun that is quickly determined to be root cause. The team seemed to be focusing on solutions that did not involve hardware changes. Changes to FDIR persistence from 2 to 5 flags set was an easy, quick solution that could be implemented in software. FDIR shutdown of thrusters masked any opportunities for additional learning, immediately becoming the focus of the failure investigation. Yeah, this definitely needs looking into in more detail. I can understand why they would go for quick do not involve hardware changes. Totally get that. Understandable, should I say, but at the end of the day, it's not enough. This is not enough. This is not good enough. Okay, so CFT mission. There we go. During the CFT mission, 5 service module reaction control system thrusters failed. Four of these thrusters were recovered after some time and hot fired to allow for continued usage in the mission. One thruster was never recovered. During the mission, investigation and testing at White Sands Test Facility uncovered that the thruster valve Teflon poppet seat could swell given exposure to nitrogen tetroxide and high temperatures. In addition, higher than expected temperatures of the NTO propellant supply lines could also have been an issue, as bubbles entrained in the higher temperature NTO can disrupt thruster performance. Findings: poppet seat swelling was identified as approximate root cause of the failures based on extensive testing at White Sands Test Facility testing. The fault tree process at the completion of CFT, which is still ongoing as of this writing, which is more disciplined and more in-depth and comprehensive than previous missions. The fault tree generated the CFT failures. CFT failures consists of 10 legs with 351 failure modes and sub-modes. Yeah, I mean, fantastic. Well done for making a really big, complex fault tree, but it's still not going to address those issues that are not failures. So do an STPA, compare the results, find out what you've found in the fault trees and how they fit into the STPA and vice versa. Thruster temperatures as seen on CFT were cooler than those found during OFT1, but several were higher than OFT2. While there is inconclusive evidence, this is believed to have occurred for 2 reasons. First, manual piloting was included as a flight test objective on CFT. This piloting caused more jet firings than previously seen on OFT2 and could have led to elevated temperatures. Also, as FDIR persistence was increased, from 2 to 5 after OFT2, that change likely led to thrusters not being deselected as quickly in the CFT mission. In effect, the change in FDIR persistence allowed the thrusters to continue to operate longer and heat more. The maximum NTO valve temperatures for each mission, each thruster is shown in figure 105. So that's interesting. So that change to FDIR could actually cause other dangerous consequences. That's very interesting. So blankety blank, can't see it, don't know what it is. SM-RCS thruster failure is a multi-variable event, as previously discussed. Yeah, I can agree with that. Temperature is not the only cause of failure. Thrusters got much hotter during OFT1 than CFT and yet continued to operate. The temperature of thrusters at failure, as shown in figure 106. As shown below, 6 of the thrusters that failed in OFT1 did so at significantly higher temperatures than failures seen in OFT2 and CFT. Yeah, so maybe temperature is, affecting parts of the control loops, absolutely. But it sounds like there are other issues going on as well. Not just, because again, when you start talking about temperatures and stuff like that, you're focusing on the control process, the physics of the situation. And you're not necessarily recognizing how that can be affected by control actions or affect the control path, in terms of heat, temperature on the various different mechanical items, And then likewise on the feedback path, how is it affecting the feedback path? If we know the thrusters are getting hot, do we actually know how hot they're getting? Do we have the necessary feedback at the right sample rate to be able to understand that? From the impression I'm getting, probably not. Okay, right. So we've talked about that. Right. Let's keep going then. So thruster failures versus temperature. That's a graph, presumably. Can't see it because it's blankety blank. Low data rate continued to make diagnosis of thruster issues difficult. The team developed improved tools to determine thruster performance based on spacecraft reaction. However, multi-axis firings with multiple jets still made it difficult to diagnose based on inability to capture chamber pressures. So chamber pressures is a very, very important part of the feedback path. And so there's a question there from an architecture perspective. Is chamber pressures really an adequate source of feedback on its own? Does there need to be another distinct feedback path that is independent of pressures? Maybe it needs to be something else. I don't know. I don't know what the design solution might be. I'm not here to tell the solution, give the solution. I'm just saying, is the control structure really adequate if we just have chamber pressures? Or do we need to increase the robustness of chamber pressure feedback? Or do we need some other kind of diverse sensory feedback? That's the question for the design and architecture. Based on what's said in this report, it sounds like that would be a positive improvement. But of course, to change that and improve that, you're potentially going to have to increase the weight of the spacecraft. There's going to be some compromises needed by the sound of it. So hopefully they've got some margin for that. Okay, recommendations. Improve the data rate for critical parameters either through changes to the current architecture, yeah, that's what I've just been saying, or additional data measuring and recording systems. Continue to refine the tools necessary to ascertain thruster performance based on vehicle reaction, independent of thruster chamber pressure measurements. Yeah. With many variables playing into thruster failures and history showing failures as low as approximately blankety blank. Is that a failure rate or temperature? I think it's a temperature, isn't it? It is critical to ensure that the thermal environment changes and improvements are planned for the next mission demonstrate significant margin. There is uncertainty as to where the actual failure temperature is, so margin is required to limit the chance of thruster failure. So in this control structure here, I was talking about the thrust control system. I'd argue that you also need, in parallel, to consider thermal control. So what does the thermal control process look like? So let's just put that over here. Spacecraft thermal state, something like that. So you've got a thermal controller controlling the spacecraft thermal state and making sure that state doesn't undermine these control loops. So however that might look. And then of course you've got telemetry to the ground team to think about. There we go. Right, let's zoom back into here. Zoom in so you can see. It is critical to ensure that the thermal environment changes and improvements planned for the next mission demonstrate significant margin. There is uncertainty as to where the actual failure temperature is, so margin is required to limit the chance of thruster failure. Lessons learned. Manual control can introduce an unconstrained demand on the system. Well, if there needs to be some constraint on it, the control structure should be making sure that people doing the manual control understand those constraints. And the system should be designed to give them adequate feedback to make sure that they stay within those constraints, or if they approach them, that they're given adequate awareness and warning to be able to do something about it before they're breached. It is not possible to effectively envelope the amount and matter in which a human pilot will operate a system. Given this difficulty in enveloping human behaviour, software systems should be used to create keep-out zones that ensure humans do not call for a system to operate outside of its qualified limits. I would have thought you'd already have that in place. Given the severity of the outcomes, I would have thought you'd have that kind of mitigation in place. And then at least have an override and an awareness for the crew to know what those limits are. But okay, maybe that's a recommendation. Okay, so now this last part is, it says systematic programmatic issues. So what I'm going to do is I'm going to put them on their own level. Oops. Like this. There we go. So we are close to the end. It's taking ages. It's because I talk too much and make mistakes. And I don't unmute myself when I'm supposed to, you know. Right, here we go. Systematic program. In fact, actually, let's just have a 5-minute break and then we'll carry on with this. Let's come back in 5 minutes. And we're back in the room. Hopefully that's working. So just looking at LinkedIn and Facebook and YouTube. Seems to be working. I've got the levels going up and down, so my audio is apparently going out. But there seems to be a bit of a lag. But anyway, let's continue from where we left off. I did say that this would be the last live stream in this series, so live stream 31. And I'm just looking at it going, well, there's still quite a lot to get through. In fact, while I'm scrolling around, I should probably show you, shouldn't I? There we go. Pardon me. Right, there we go. So we've got these 3 pages to do. And then we've got some blankety blank pages, which will take 2 minutes. Then we've got another couple of pages. We've done that page already. We've got some acronyms, a couple of appendices with a few pages. So we're probably about 15 pages of text to go. And it is 10 to 8. I think I'm going to push and get this done today. So if you'll bear with me, we'll keep pushing and we'll go for it tonight. And while I'm talking about that, let me just remind you, if you want to go join me on the workshop, please join the waiting list. I will add that join waiting list to the chat so you can see it. I'll stick it in. There we go. So you can see that. So please join the wait list and then I'll send you an email when the event's ready and we'll crack on. Right, okay, here we go then. So these are the systematic programmatic issues that the data team highlighted. Now, before we go into this, I just want to observe something, and maybe it's dealt with here. But there was some discussion about the telemetry feedback to ground and that it wasn't really good enough. It wasn't really fast enough. Fantastic. But this report doesn't really go into the detail of, well, what telemetry, what speed, what data rates, why it was considered inadequate. And again, it is a publicly available report, so maybe that's the reason why they've not talked about it. But it is just interesting. It is interesting why it's not really discussed in that much detail. But anyway, let's keep going. So, systematic programmatic issues. There are many issues have been identified by the SDRT that apply across all the missions reviewed. Poppet seat swell is an historically documented and known issue for this type of thruster. So it's a known issue apparently. Many examples of Teflon poppet seat swelling were identified by the NASA propulsion team and reviewed by the SDRT. These include a Gemini, attitude control anomaly investigation from 1967. Makes the statement, known issues of performance degradation included NTO, nitrogen tetroxide vaporization, thermal distortion, Teflon valve seat swelling, NTO flow decay, etc. The high temperature critical part of the TCA valve is the Teflon seat, which, if subjected to high temperature, may swell. If excessive, this swelling could restrict propellant flow. Okay, fantastic. There's an example that's there. So was that or was it not included in the consideration of the safety assessment and design of this propulsion control system? Yes or no? If it wasn't, why not? What is the control structure that meant they didn't get that information? Or if it was known and available, what difference did it make to the design? Because it may be that they knew all about it and discounted it for some reasons. Maybe they were valid reasons. But the investigation should establish that. Shuttle Auxiliary Power Unit HOPE-X program. In 2000, Had acceptance testing failure, which with this exact failure mode, poppet seat swelling. So this is the same thing. So again, this is focusing on the poppet seat swelling. Yeah, well, of course, yeah, okay. This finding is particularly interesting because it occurred after the poppet seat had only been exposed to water, not nitrogen tetroxide at ambient temperatures, not elevated temperatures. In other words, Teflon poppets out of this geometry can demonstrate swelling without propellant or high temperature exposure. This valve was also built by Moog, the Starliner propulsion system valve manufacturer. Interesting. That is interesting. Wideband global SATCOM failure investigation found the pressure data of the wideband global SATCOM anomaly pointed to a reduction in oxidizer flow, and thus the focus turned to swelling of the Teflon valve. Mars 71 anomaly investigation found seat deformation was exacerbated by high soak-back temperatures and exposure to propellants. NTO suffered the seat more than MMH. I can't remember what MMH is. In fact, if I have a look, where is it? Boeing Starliner. Source materials, investigation report, MMH. It's probably not in there, is it? There we go. MMH. Monomethyl hydrazine. That's what that means. And it is pretty nasty stuff, if I remember correctly. You don't want to get that stuff on your skin. An American Institute of Aeronautics and Astronautics paper states both model and experimental data show that PTFE seal extrusion can be caused by thermal cycling alone without the intervening influence of oxidizer. Furthermore, thermal extrusion is accompanied by gap formation. Okay, so that's poppet seat swell. So if we were going back over to look at the control loop on here, we're talking about impacts on the control path. That's where the physical analysis would consider the thermal aspects of the poppets and the effect of the NTO thermal distortion and NTO issues. Okay, so early in development, commercial crew and commercial partners implemented a review process, and participants created review item discrepancies, or RIDs, RIDs. Unfortunately, major RIDs created by NASA during reviews were combined with Boeing-generated RIDs The Boeing RIDs did not have the same depth required actions as the original NASA RID, and Boeing RID closure only needed acceptance from the Boeing author. Oh wow, okay, that's interesting. During the design review cycle, several RIDs were submitted that identified concerns or issues regarding the service module propulsion doghouse thermal environments. These were then combined with Boeing RIDs that did not have a clear documented closure. Okay, so this is an administrative function that is absolutely critical to the safety of the program. And so, the investigation should go and have a look at how RIDs are created, treated, and managed, and there should be recommendations for that. And I imagine that same issue exists across multiple programs, not just this one. There are a number of requirement sets that are applicable to the development of the propulsion system. However, many requirement gaps remain. SMCS 016 is applicable but lacks sufficient details on qualification hot fire testing and does not enforce a requirement for this type of test. Right, well, that needs fixing. NASA Standard 5012 also lacks specificity on qualification hot fire testing. Okay. NASA STD 6001 is an applicable materials specification, and it specifies, selection of fluid compatible materials. However, it lacks sufficient details on material selection and interactions. SMCS 25 is a propulsion system level requirement set. But states it is not applicable to small engines like the SMRCS thrusters. So when we say small engines, what do we actually mean? And why isn't there a small engines equivalent to that? Why was not one made available or created? Again, bad requirements, inadequate requirements, is always on the hook in large accidents like this one. So what does the control structure look like for the generation of requirements and ensuring that requirements are fulfilled and have appropriate verification, validation, and testing associated with them? Who's doing that? I'm pretty sure there'll be a requirements management function of some description. Integrated doghouse thermal qualification testing was never baselined. OFT1 was planned to provide thermal qualification of the doghouse. Throughout the Starliner development phases, the propulsion thermal model maturity was a concern, as it lagged the overall service module propulsion system design maturity. In other words, the propulsion system design was finalized before the thermal analysis was completed. I mean, that's just ridiculous. So what is it about the way the program was managed that contributed to this? Where is the investigation of that? And, what are the constraints put in place to ensure that that doesn't happen again? Yeah, we need to figure that out. There needs to be a recommendation for that. Thermal module maturity was a concern from the first service module propulsion system level design review. Boeing was behind schedule throughout the design process, which again is a normal thing for big complex programs. Data was not at a commensurate level of maturity indicated at multiple reviews. Boeing did not effectively communicate service module propulsion system duty cycles or planned usage to the propulsion system designer, Aerojet Rocketdyne. Okay. So why was that then? What we're going to do to make sure that happens in the future? I mean, what did Aerojet Rocketdyne do? I'm pretty sure they would have been screaming and saying, look, we need this information, or we're going to have to use assumptions and you're going to have to cover deal with the consequences. Boeing. Thermal concerns were never raised to NASA mission planning meetings to discuss alternatives to reduce RCS heating. Thruster usage and mission parameters were not coordinated with the propulsion system provider Aerojet Rocketdyne. Thruster performance is complex, multivariable issue. It is an interrelated combination of temperature, duty cycles, total firing time, OMAC usage, valve poppet, seat geometry, valve poppet stroke clearance, etc. Testing any one aspect, or maybe even a few of these together, may not lead to a true solution with margin. Yeah, absolutely, yeah. Recommendations. Given this multivariable problem, a robust Delta qualification test program will be required. Is required. Must be. Must happen. Temperature alone, while important, is not the only parameter of interest to be enveloped during testing. Lessons learned within individual companies as well as across the spaceflight industry are not well captured or consulted during new hardware builds. CCP should work to implement a robust lesson learned process to be flowed to commercial providers. Special attention must be paid to thermal models and their certification validation. Models must be reliable and predict environments conservatively to ensure design selections based on their output are appropriate. Lesson learned. Lesson learned within individual companies as well as across the spaceflight industry are not well captured or consulted during new hardware builds. NASA should work to implement a robust lesson learned process to be flowed to commercial partners providers. With respect, those commercial partners providers should already be doing that themselves anyway. And I can understand if they don't have access to lessons learned by NASA and documented within NASA, and that needs to be shared. But they should always also be responsible for making sure this happens. Okay, disposition of all RIDs needs to be approved by the author and reviewed at a program control board or equivalent forum to ensure that all concerned parties concur the issues identified have been adequately addressed. Yes, I agree. But again, that's what the process should have been doing in the first place. So why was that not happening? Why did that break down? Okay, building a propulsion system based solely on high-level component requirements is insufficient and misses interactions, integrated effects between hardware and the usage environment. Hardware, software, human factors, environment, the whole shooting match. Requirements by themselves are insufficient to cover design-specific solutions. Spacecraft missions cannot be enveloping of all possible flight environments and scenarios, and flight test is not an acceptable substitute for a robust ground program. Absolutely. I absolutely agree with that. Thermal models and thruster usage were not adequately integrated between Boeing and their propulsion system designer Aerojet Rocketdyne. So this is thermal models and thruster usage. The SM-RCS thrusters were considered to be off-the-shelf hardware, because of course they were, but the actual usage environment was never compared to historical usage to understand if these thrusters were suitable for the Starliner usage profiles. Fantastic. So it was never compared. So whose job is that to do exactly that? And why was it never compared? Why would it make sense for them not to do that? You know, has something been lost in translation, or, you know, what's the situation? That needs to be fixed. Because again, that issue is not just constrained to thrusters. It is a principle, an engineering principle that could apply across all different types of components that are off the shelf. But yeah, okay, so that's the systemic programmatic issues. We've done that now. So what I'm going to do is just mark off where we've got up to. So we've done all of that. We've done all. No, it's not that one, Simon. It's this one. No, this one. Right. So we've done all of that. Done all of that. We've done that bit. So now we're at the senior review panel. So we've got like a few pages left now. We are genuinely close to the end. Fantastic. Right. So let's zoom out. So the next section is the senior review panel review. So we've got some senior review panel members. We've got 1, 2, 3, 4, 5, 6, 7 people, apparently. We don't know who they are. We don't know the detail. Like I said before, it would be nice to have at least an inkling as to who these people are, what their background is, but I can understand why it's redacted. So we've done that bit. Oh, there is a summary. So there's 3 pages to summarize it. So let's read this then. So this is the STAR Senior Review Panel Summary. There we go. Right. So it's to somebody. We don't know who. And it's from the STAR Senior Review Panel. And this was done on the 4th day of the 29th month, 2025. It was the STAR Senior Review Panel review, peer review closeout. So their final bit of work, which is interesting because this was completed apparently before the pit investigation was completed. And I'm sure there's some dates in May 2025, and the pit review, I think it was reviewed up till December 2025 into the new year of 2025. And the pit review team also was supported by the STAR Senior Review Panel peer review closeout. So it's interesting. I don't know why there's a difference in the dates. It would have been nice if there was a Gantt chart that showed when these different reviews were done and if they're ongoing and what their reports were, their deliverables, when they were issued, reviewed, and all that kind of stuff. It would have been helpful to get a clearer picture. So there we go. Per the STAR Review Panel Charter, STAR Senior Review Panel Charter. So that'll be some kind of document somewhere, which will describe what the charter was for that senior review panel and what they should do and not do. The panel has participated in recurring peer reviews of the STAR team products. This includes an overview of the data collection process, including interview feedback. It also included interim products that organise the feedback, findings and recommendations around themes, as well as the final written narrative integrating the STAR final product, which is the report we've just finished reading. These peer review efforts were conducted over a series of meetings on approximately a monthly cadence, beginning in December 2024 and concluding with the review of the final report in April 2025. The senior panel members remained constant during this effort, though not all members were present at every interaction. The panel members were these blankety blanks, which again I'm assuming tally with these, as you can see here. Through monthly meetings, the review panel had the opportunity to see some of the details of the STAR team interviews, from which the final STAR team conclusions were drawn. The STAR team interview data revealed a number of themes that were not considered in scope for the STAR team investigation, which the review panel found to be important themes to include as NASA looks at how to best incorporate the lessons of the Starliner crew flight test mission. NASA and Boeing launched several concurrent investigations associated with CFT, and the STAR investigation itself was fairly limited in scope. The stated intent of agency leadership was to launch a parallel investigation into the organizational factors that influence the outcome of the CFT crew flight test, which has been transitioned to a program investigation team. Right, okay, that makes sense. And currently ongoing as this STAR investigation comes to a close. Okay, so the STAR investigation finished as the PIT team, program investigation team, got stuck in. The review panel will remain intact to advise the CFT PIT as they complete their investigation. Right, okay, so that makes sense. Though the STAR investigation focused tightly on Starliner's service module propulsion system issues, a number of the findings, recommendations, and lessons learned provided by the STAR investigation are general in nature. The review team recommends that CCP and Boeing apply those recommendations and lessons beyond Starliner's propulsion in an effort to gain the greatest value from this investigation, reduce the potential for finding similar issues in other Starliner systems in future flights, and provide maximum value to the agency across our portfolio of development and operations. In reviewing the data and results of the STAR investigation, several themes have come into focus that the review team considered in a broader context. The interview data from the STAR investigation revealed a number of organizational and cultural aspects of decision making, briefly touched on in the general findings section of this report. These items of interest influence the final outcome of crew flight test. The review panel finds merit in further detailed investigation of these themes. Yeah, okay, sounds great. Many of the STAR investigation recommendations require a greater investment of personnel and/or hardware in the form of greater insight and communication during product development, review approval of supply chains, and sparing strategies, as well as dedicated focus on flight-like hardware test campaigns. The review panel observes that currently a number of Starliner test topics are making their way to the Crew Commercial Program Control Board, each with the same challenges: limitations on available hardware and test facilities that would limit the ability to run flight-like tests. The review panel agrees with the STAR investigation team recommendations, but finds that the commercial crew needs to address how to change decision-making processes going forward when called on to navigate similar challenges now and in the future, and otherwise the lessons of CFT will be lost. A final theme centers on the idea that NASA requires 2 independent providers for crew access to low Earth orbit. This redundant capability requirement produced an over-constrained system. I don't know what they're going to say on the next page, but I would have thought that this has demonstrated why NASA needs 2 independent providers for crew access to low Earth orbit, and that there must be sufficient independence between the two. Well, let's see what it says on the next page. Two providers were selected for commercial crew contracts, and NASA required that both be successful. Resource constraints, and perhaps in the case of Starliner, an over-reliance on the promise of heritage hardware and software, and the requirement of success ultimately led to a smaller effort in testing, reduction in design iteration, and erosion in the norms of flight rationale and standards for risk acceptance. If every provider must be successful, and NASA is unwilling or unable to fund improvements, and then force or alter contracts to ensure success, it is inevitable that standards will be lower, increasing the chances of failure. Yeah, I understand, and I kind of agree. I agree. In the topper layers of the control structure, if the senior layers in the control structure are placing unreasonable demands on the lower parts of the control structure, such that the lower parts are not resourced or capable of fulfilling those needs, then yeah, I agree. However, the safety process they applied, the fault tree analysis and all of the other good stuff, if it was supplemented with STPA, I think a lot of these issues could have been addressed, dealt with. But it's important to recognise that typical safety assessments focus on the technical architecture of the product, service, or system, not necessarily the organisational issues, interactions, and structures that obviously contributed to this accident. So I'm not suggesting STPA will solve all of it. I'm not saying that, but it will certainly help tremendously. But, at the end of the day, the organisations at the top, they must provide adequate resources for that control structure to be successful. And if they're not doing that, then feedback needs to be passed back. And where there are situations where things cannot continue because the resources are not there, then that has to be escalated. And it has to be escalated with the potential to stop the program or pause the program. And I know that that's a very, scary thing to think about. But sometimes on big programs, that decision has to be made. And that's what the big bucks get, people get paid the big bucks for. Happy to think and talk about that a bit more. It is the review panel's overall assessment that the STAR investigation did a commendable and thorough analysis with its given limited scope. Yes, I agree with that. Great work, great analysis, but please use STPA and CAST, please, in the future. Because I don't think we've learned enough from this. I think we're missing some key things from a technical standpoint and also an organisational and a program management perspective. I think we're missing a lot. Their recommendations are stated as explicit for commercial crew to implement before the next flight or as practical, which the review panel endorses. Fantastic. The review panel finds that the commercial crew program should develop and share a post-investigation implementation plan and a timetable to ensure subsequent Starliner missions benefit from the crew flight test experience. The review panel encourages that lessons learned be shared with other NASA project managers widely and immediately in order for them to make any applicable and necessary changes. Lastly, the review panel looks to the pit to explore the themes stated above. Okay, so the pit, the main body of this report, as opposed to the STAR team and SDR team reports in the appendices, the main body of this report is the pit investigation, which did explore those themes. So it's a bit of a back to front way of reading the report. Really, we should have learnt about the STAR team and the SDRT team reports and findings and themes before we went into the pit. And I suppose that explains why the technical part of the pit report is not as detailed as I was expecting. Fantastic. Right, so we've done that bit. Let's tick that off. So we've done that. There we go. Right, so the only thing we have to do now is the appendices. We already did the conclusions the other day. I don't think we need... I mean, the conclusions is literally that. That's all it is. 3 paragraphs. Actually, yeah, let's just talk about this for a minute. So commercial crew accepted risks in the service module propulsion system and the command module propulsion system that were not fully understood prior to crew flight test. These risks included variances to requirements and unexplained anomalies from the previous flight tests. There were no unstated technical concerns amongst the NASA team during the commit to flight process, but there was a shared underestimation of the likelihood of thruster failures. So I'm hoping, based on what you've seen today and when I built the control structure model and started to talk about it, that actually it's not just failures that we need to be thinking about. And when we're trying to, bullshit ourselves with putting likelihoods and risk assessments associated with these, we just have to take a step back and say, well, look, if we're only looking at things through the lens of, failures, and then we're going to try and put some magic numbers on it, we're deluding ourselves. If we're going to start thinking about dangerous successes as well, and understand that likelihood is, considering likelihood is really not going to help us, it is a distraction, that would be a better position for us all to be in, if that makes sense. Right, so let's just take a step back then. So we've done that. So let's just have a quick look at this. So there is Appendix A is a acronym list, as you can see. So there's AR, Aerojet Rocketdyne. Trying to think if there was any other acronyms we needed to think about. I don't think there is. So Appendix B, what's this then, everybody? Appendix B is the interviews, summary of interviews. Right, so this could be really helpful because this might suggest some candidate controllers for including in our control structure model. So let's just have a look at that. So we've got program managers and deputies, both former and current. We've got the CCT CAP source evaluation board members, CCP office managers and deputies, spacecraft propulsion leads and experts, safety technical review panel chairs, certification manager, verification and validation panel chair, flight operations directorate, FOD, Starliner crew, flight directors, mission operations, JTT chair, engineering, chief engineers, spacecraft leads, spacecraft valve experts, spacecraft thermal experts. What about propulsion control experts and flight test instrumentation experts? Maybe they'll come later. S&MA, safety and mission assurance, I think. Let me just check the acronym list. S&MA, was that a good guess? Yeah, look at that. Perfect guess. Space and mission assurance. So chief safety officers, former and current. Right, where's the safety engineers in that list? Where's the people who did the fault trees? Where's the people that made the decisions to accept these things? Interesting. Right, support posture. Oh, so these are the questions themselves. This will be interesting. And I don't know why there's a blank page there. So this is the STAR interview questions. So STAR interview questions. I think there's a time lag between me writing and it coming up on the screen. So that's the STAR interview questions. And this is the SDRT interview questions. Pardon me. Yeah, this is not as good as an iPad. Anyway, there we go. Right. So, support posture. When did you support CCP and what was your role working with Boeing? Was CCP your primary responsibility, Boeing CCP? What percentage of time were you spending on CCP? Did you participate in mission support and or flight following? Referencing the timeline in the pre-read materials, are there any observations you would like to share? Okay, so this is establishing how they interacted with the CCP and Boeing. and these are not Boeing personnel by the implication, these are NASA personnel. CCP programmatic. Please describe your understanding of the insight oversight philosophies during your involvement through the CCP lifecycle and program leadership. Due to the limitations governed under this SAAs, did this prevent NASA from providing feedback needed to influence the design? If in CCP prior to CCT CAP, what was your perspective of Boeing and SpaceX ability to implement certification of a human space transportation system? Do you believe that the CCP 11130 requirements were adequate? Do you believe that the CCP design and construction standards were adequate? Do you believe that the CCI CAP or CCT CAP deliverable requirements were adequate? Do you believe that the CCT CAP insight data deliverables were adequate? Do you believe that your team had sufficient expertise and resources to perform your insight and oversight roles on CCT CAP? Service Module Propulsion Certification. Do you believe that the Service Module Propulsion System hazards were adequately understood prior to CFT, not looking for 2020 hindsight? Describe the NASA review level of hazard verifications throughout the process. Did you believe that the SM propulsion system software, including FDIR, was adequately understood prior to CFT? Do you believe that the Service Module Propulsion System environments were adequately understood prior to CFT? Did you believe that the Service Module Propulsion System hardware design was adequately understood prior to CFT? Did you believe that the Service Module Propulsion System performance was accurately modelled prior to CFT? Did you believe that the risks of the Service Module Propulsion System were accurately characterized prior to CFT? Did you believe that OFT1 and OFT2 in-flight anomalies on the propulsion system were adequately resolved prior to CFT? In your opinion, were the Service Module Propulsion System designs finalized too early, too late? Did we have adequate reviews prior to design implementation? Did we have sufficient ability to effect change on the design process? Was the program governance for shared accountability and requirements flowed down? Adequately applied to Boeing outsourcing of propulsion system to Aerojet Rocketdyne? And their suppliers for DDT and E. Was the program governance for shared accountability? So this shared accountability is this safety management system sort of description of how they want to share NASA accountability with the supplier, in this case Boeing. And I don't believe that shared accountability model was actually appropriate. I think it was fundamentally flawed and needs to be re-engineered. So was the program governance for shared accountability and requirements flow down adequately applied to Boeing outsourcing a propulsion system to Aerojet Rocketdyne and their suppliers for DDT and E? Based on reading this report, my view is that the answer to that is categorically no, and there needs to be a huge, reconsideration of how that's actually done, and that includes reviewing the various contracts between those entities to make sure that those contracts aren't inadvertently strangling the importance, the flow of important information, and the decision making that needs to happen. Do you believe that the team focused on the right products to evaluate certification, or should we have different priorities? Phase safety review, VCN's variances. Do you believe there were propulsion system decisions made due to unrealistic schedules during DD and T and E? Interesting. I've just got a comment there from Crystal. Hi, Crystal. I'm amazed you're still with us. Thank you for your tenacity. These are 99% closed questions and self-incriminating if answered honestly. They are closed questions, but I would anticipate that this list has been generated at the beginning and then updated as they've progressed with the investigation, and they are questions to start the conversation, or at least that's how I would interpret this, though I don't know that to be the case. I mean, it could be that someone's just got a big list of questions and thrown them at the wall in the interviews to find out what sticks. And if that is the case, that's not really appropriate at all. That does bring into question the integrity of the investigation and the interviews. But I'm maybe naively assuming that they have done all the interviews appropriately, and these are just some of the main questions that they need to ask. But yes, the observation that they are closed questions is a very good one. And again, in a certain environment, in a certain culture, they could be very incriminating, and people may feel unable to answer them truthfully or accurately. And of course, as investigators, all of us as investigators, we have to be respectful of the people we're interviewing and the situation they may find themselves or see themselves. And we have to facilitate them to be able to answer the questions as completely and truthfully as they can, whilst also protecting those witnesses, if that makes sense. So yeah, I've just assumed this list is a list of inspirational questions, not necessarily how they would be delivered in an interview. But if they are delivered this way in an interview, of course, that's a bit, a bit questionable. But again, they did do these interviews. In fact, actually, let me just rewind what I'm about to say. In the PIT part of this investigation report, the organizational focused investigation team, which wrote the main body of this report, they did all of their interviews between, I think it was April and May or June 2025. So they did an incredible amount of investigation, interviews during that period of time. And then this list we've got here, I think this list is the list of questions that the STAR team did as part of their investigation, which they completed in April, May of 2025. So it's before the PIT team did their, interviews, if you like. But again, this whole report is not that clear. It's not that explicit. I mean, it could be that I just don't know what I'm looking at and I've completely misunderstood it. That's always a possibility. But yeah, thank you for making that comment. It is incredibly important how we conduct ourselves as investigators and how we ask questions. And asking close questions is not necessarily a good way to do things. It can seriously limit and undermine the value you can extract from an investigation by asking close questions. There we go. So, but again, like I said, these could be scene-setting questions to help the investigators understand where this interviewee actually sits in relation to the accident itself. Qualification testing. Did you participate? Actually, before we continue, Now, there's been nothing up to this point. Well, hang on. Let me wind back again. So, as a system safety engineer that would do fault trees and FMEAs and all of that good stuff and safety cases, and help set requirements and set testing requirements for verification and validation, how we're going to test stuff, how to identify, analyze hazards, how to generate requirements for fault trees, all of that good stuff. There are no questions here that would strike me as the questions you would ask the safety engineers. And that leaves me a bit cold and a bit confused because, there's a lot of mention of fault trees in this report, and yet none of these questions really focus on the conduct of those analyses or the way that those safety activities were performed and the challenges associated with reviews. And even the mention in the previous live stream about one of the NASA guys or girls sending emails to say, hey, there's an issue, and then repeatedly sending that email on a number of occasions over the best part of 5 years. I would kind of expect these questions to address some of those topics. They are certainly the kind of questions I would ask, but then I'm biased because I'm a system safety engineer. Things like, it says here, did you believe that the SM propulsion system hazards were adequately understood prior to CFT? Another question is, well, were those hazards actually defined appropriately? What was the process for defining those hazards? How were they reviewed and signed off? What are the associated safety requirements related to those hazards? What safety analyses methods were used to analyze those hazards and set requirements? Who reviewed those safety analyses? What were the review comments? Were there outstanding review comments that were not addressed? I mean, it mentions earlier on today about the RIDs, the RIDs, the review item comments that NASA made, but that they were not fulfilled. They were closed off by Boeing. Right, okay, let's keep going. So, qualification testing. Did you participate in or evaluate the propulsion system qualification testing? Did you review any of the subsystem qualification specifications from Aerojet and suppliers? With hindsight knowledge, what would you have changed in the qual testing to prevent the anomalies uncovered during CFT? Use STPA. Did the team... I should get a button on my thingy that splashes up on the screen. Use STPA. Anyway, with hindsight knowledge, what would you have changed in the qual testing to prevent the anomalies uncovered during CFT? Did the team consider doghouse qualification testing? Did we have adequate instrumentation in the test flights to validate qual or flight environments? M&P specific questions. So M&P. What is M&P? Does anybody know what M&P is? Should we have a look at the acronym list? Where's the acronym list? Where's it gone? Have I skipped over it? Oh, there it is. Right, M&P, everybody. M&P, where is it? It's not in the list. Of course it's not. Of course it's not. M&P. Okay, don't know what it is. Can't remember. Okay. Let's keep going. Was M&P involved in the propulsion system design reviews under CCI CAP? Was there any significant findings, comments? How does the MIUL MUA process cover the SL1 propulsion system components from AJR? What about their suppliers such as Moog? So AJR, I think that's Aerojet Rocketdyne, and Moog is another company, a supplier. These MUAs, MIULs, I think they are to do with material specifications. Of course, that's not in the acronym list, because why would it be? Yeah, there we go. Material usage agreement. That's what that means. And I can't click on it. Why can't I click on it? There we go. Paste. Look at that. Fantastic. Right. A summary of the material usage agreement progress came forward to the PCB Program Control Board before the orbital flight test. Why wasn't there a subsequent briefing for the other test flights? Do we receive material usage agreements prior to the crew flight test for the blankety-blank helium O-ring within the RCS thruster flange or the Teflon poppet seal within the RCS thruster? If so, what category MUAs were they? Did we require hypergolic exposure testing for soft goods within the Starliner 1 propulsion system, particularly for the RCS reaction control system portion of the system? If not, why did we continue allowing analysis in lieu of testing after earlier compatibility issues with both providers? Closing, do you have any comments that you would like to make? Yeah, closed questioning is when I did my investigator training, I don't know, 10 or so years ago. The main point the instructor made was, we don't use closed questions until we're, quite down the process, the flow of asking questions. We try and be as open as we can. And then when we're touching on particular topics or pulling on particular threads, then we try and be a bit more focused on it. But it would be a case of, what comments would you like to make? Let's assume they've got some comments they want to make. Let's hear them. But again, these questions are quite specific, but I suspect this is a subset of the questions, not the full set. It would be nice to know if they had proper investigators that know how to do questioning and interviews appropriately, because it is a very delicate art. It is a dark art, you could say. And of course, you've got to be really careful asking people questions where you might inadvertently overwrite their memories. You might ask them questions that trample all over everything that they remember, and then they can't remember properly anymore. So we have to be really careful with how we question people. But again, the people that were asked questions that are written here are not everybody involved in the entire program. This is just the NASA personnel involved. Okay, so we've got the SDRT, which is the Starliner Data Review Team questions. So the background of the SDRT charter is to examine the detailed data from the orbital flight test 1, 2 and the crew flight test, and focus on how the anomalies from the previous missions were resolved or accepted for continued flight. That is not what the SDRT part of this report actually talks about. In fact, it barely even, this bit, focus on how anomalies were resolved. It touches on that, but it's not satisfactory in my view. And it certainly didn't talk about this bit. There was no discussion of that I just read today. What are your thoughts? Because I don't think that was discussed in any kind of detail. Because who are the stakeholders that are accepting the thing for continued flights? You've got the Boeing part of the control structure, you've got the NASA part of the control structure, and you've also got the operations part of the control structure. And there was no discussion in those previous sections today that actually addressed those three areas. Anyway, the main goal was to understand what data the teams reviewed. Well, it doesn't say that in that section. It doesn't explicitly say a list of the data they reviewed, or the conclusions that were drawn, what data might now be looked at with perfect hindsight in a different light, and probably most importantly, is the CFT data being looked at correctly, or is there something else that should be considered in regard to CFT? I don't think that part of the report does that. Unless there's another report somewhere that's not publicly available, what's in this document does not cover that in adequate detail. My humble opinion. Background. Tell about your experience with Starliner, which missions you supported directly, and current role for Boeing missions. OFT mission. 12th of the 20th month, 2019. Focusing on the service module reaction control system thrusters, it appears to the SDRT that the high duty cycle overuse of the thrusters led to temperatures beyond qual that caused pressure transducer shift failures, solenoid failures, and thruster shut down. The root cause was determined to be the mission elapsed time anomaly, thruster use outside of expectations, and qual, and that fixing the MET anomaly would eliminate future failures. What was the anomalous OI burn, orbital insertion burn, mission elapsed time anomaly, and what do you think was affected? See, these are very different questions. These are much more open. Were there any discussions at the lower working team levels with Boeing that weren't added to the future charts for program level meetings? Do you think that the MET anomaly concealed any deeper fundamental issues with the thrusters, and or did the team write off thruster issues as being solely caused by this anomaly? I really like that question. I think that's a good question. If I was to answer that based on what I've read in this report, my answer would be yes. The MET anomaly and the way it was investigated concealed other deeper fundamental issues. Deeper fundamental issues which I believe STPA can help you find, dig out, and do something about. And I would be honoured to provide that support. Were lessons learned from the flight and the method of anomaly resolution thorough? No. What post-flight procedures address root cause of the failed thrusters? Proceedings. Do you recall the origin of the fault tree and internal discussions of its elements? What agreements were made on corrective actions? What agreements were made on corrective actions or additional testing for OFT2, Orbital Flight Test 2? There are specific references to recommend ground testing of RCS thrusters to assess impact of the OFT Orbital Flight Test duty cycle on the chamber pressure sensor operation. Was any additional testing completed post-orbital flight test to better characterize thruster performance and temperatures or improve thermal models? Reference offline action 2, recommend ground testing of RCS thrusters to assess impact of orbital flight test duty cycle on chamber pressure sensor operation. There were also notes that the team, was now sensitized to high jet pulse usage. Were any changes made to reduce the number of jet firings, increase pulse durations? Okay, and then finally for OFT2 mission, so this was the 19th of May 2022 to the 25th of May 2022. For this mission, the SDRT would summarize the outcome of this investigations and changes made to be that the data rates and thruster ramp-on rates, the root cause of failures was believed to be FDIR failure or strikes. Okay, everybody, I think we've found something really, really interesting just here. Bear with me a second. So earlier on today, in this live stream, we were talking about this control structure here that we chucked together. So at the bottom, the control process is obviously using the thrusters. And as part of that control process is the thruster chamber pressure. And that chamber pressure has some kind of sensory feedback. We don't know the detail of that. And it provides that feedback to the integrated propulsion controller and the flight management computer. And that chamber pressure has criteria of less than 110 psi A is taken as off or degraded, or chamber pressure above 110 psi A is on. And then, of course, we've got mission elapsed time, availability table, and the thruster status, and then the failed off flag And then, of course, we've got this thing called an FDIR, fault detection, isolation, recovery scheme, which is essentially the decision making, the control algorithm for this controller, and whether it shuts the thrusters on or off, or sets them as failed off or not. And that flag is based on two issues. If it has two issues, it will flag them as failed. And then they later change that software, that algorithm, to change that flag to 5. So if there's 5 issues, it'll be flagged as failed, whereas before it was only 2 issues. Now, the point I wanted to make, and I'll just zoom out so I can do this. The point I wanted to make is related to the type of, there it is, that one. That is exactly the one I want. So let's zoom back down here. Let's go to here. Right, let's just delete this scribble. So we've got no scribble on it. There we go. Right, look. So these are timing diagrams, and I need to update this because I've had some feedback from a training session recently with non-engineers that are not familiar with timing diagrams. So if you're not familiar with what these are, let me explain. So if you imagine that you've got a graph, and this graph along the bottom is the time. So if you start here, time equals 0, and as you move towards the right, time gets bigger and bigger. So let's say that's a time period of 10 seconds, let's say. So if we go to 0 to time equals 4 seconds, we want, what our intention is for the system, whatever it is, to provide a control action at t equals 4 seconds. We want to turn the thrusters on, whatever it is. So we turn the thrusters on, and then for 2 seconds they stay on, and then we turn the thrusters off. That's what we want the system to do. That's why this line is green. So it's off, it goes to on, stays on, then it goes off again. That's the intended function. Now, if we do not provide that control action, for whatever reason, whatever context, we would refer to that as a control action not provided. So it's this red dotted line. Now, if we think about the same graph, I've just noticed, the same graph, but this time we've got a situation where we do not want a control action. We don't want one. There should never be one in a certain context. So this is our intention. But for argument's sake, something, 4 seconds in, the controller provides the control action. So we've now got the control action, and it lasts for a period of time, let's say 2 seconds, and then it disappears again. In this scenario, we've got the control action when we didn't want it. It's been provided, and with a particular context, this is an unsafe control action. Now, what I'm trying to stretch your mind to think about is, if this is your intention, we want the control action here for this period of time and then to disappear. And anything that is other than that, if it's too early, it's too late, it's too long, too short, too much, too little, then that is an unsafe control action by definition. Now, you'll have noticed that these are all 90-degree lines. They're just, we've got a demand, boom, it's on 100% perfect in a microsecond, a millisecond. It stays on, and then it's immediately off again. Now, that's not how the real physical world works. Sometimes it takes a bit longer than that. So let's go over to this one here. Oh, there we go. I've already got it. I'll delete that line. I'll draw it again myself. Right. So imagine timing. Imagine that this is what we want. We want the control action. Then we want it to be instantaneously on, and we want it to be instantaneously off. Now, if we're talking about timing early, if we get it early, it's a problem. If we get it late, it's a problem. But what about if the timing is like this? So instead of getting an instantaneous one, we actually get a line that goes like this. It takes a little bit of time, whatever time that is. Let's say it's, I don't know, half a second, something like that. So instead of getting the control action here, we're getting it here. And that distance, is that a problem? Is that going to cause us a problem? What about if we want to stop the thing? There we go. That's not right, is it? Come on, Si, you need to swap it around. Where's the flip? Is there not a flip option? Can I not flip it around? No, I can't. I'm just going to have to redraw it. Okay, right, here we go then. So let's imagine that when we decide to remove the control action, stop the control action, it takes time to return back to 0. What happens if we have a really cold day? What happens if it's a really cold day and instead of it taking this long to start up, what if it takes that long to start up? And then we have this same amount of time there. And then what if it takes, there we go. What if it takes that long to stop? I'm not doing a very good job here, but I hope you can see what I'm trying to do. So what if it was like that instead? Oh, no, don't want to do that, Simon. Plumb my neck. There we go. So if this is the ideal situation, the green line, it's immediately on. It's on for 2 seconds. It's immediately off. And what if it's... actually, I've drawn that wrong, haven't I? It should be there like that. I'm trying to get it proportional. There we go. Look, so if the blue line is the real normal day performance, turning on and turning off, is that going to be a problem? What about the red situation? Because this red part here, this blue part here, they are the same time that the original one is. The difference is how quickly, the onset of the control action and the offset of it is. So is the blue one okay, but the red one is not, even though they're on for the same amount of time? And what if it is a combination of these? Let me zoom out and I'll redraw it again, sorry. What if it's a combination of these? So actually, we get a slow red response. I can't draw this today. What if we get a red response like that instead? So it takes a while, it takes longer to start, and then it stays on the right amount of time and then stops more quickly. Or what about if it goes quickly and takes longer to stop? So it's like that. What if it's like that? I hope that makes sense. I'm sort of mixing lots of things there, but I'm just trying to get you to think about, not just control action not provided or provided, but what type of provided is it? Is it timing early, late, duration too long, too short? Is it sequence? Or is it to do with the ramp up and the ramp down, and the extension of the time at the top? So just have a think about that for a minute, and let's just go back to this comment down here. Where is it? So this says here, for this mission, the SDRT would summarize the outcome of this investigations and changes made to be that data rates, so that's the number and the amount of data that's provided in a period of time. So the lower the rate, the less data, the less understanding of how the system works. The higher the data rates, the more that you can see the spikes in the graphs I've just showed you. Thruster ramp on rates, so that's the angle that they ramp on. So if they ramp on very quickly or they take longer and then also down again. The root cause of failures was believed to be the FDIR failures or strikes. So it could be, I'm just zooming out again, sorry. It could be that this feedback, it has a time delay in it. So it's this red one. So the FDIR control algorithm may be expecting a nice quick ramp like this, but the reality of the situation is it takes longer. For whatever reason, it takes longer. And so the FDIR believes that it's faulty when it's just taking longer. And so it marks it as faulty twice, and then it disables it completely. but it's down to the physics of the control process, down to the way that the sensory feedback is provided. So yeah, for me, doing STPA on this bit alone would, help solve this problem. I'm certain of it. Increasing persistence on the number of strikes required to fail a thruster was believed to have eliminated the nuisance faults. Well, again, it's not eliminated the nuisance faults. Well, I suppose it has, but the reason there are nuisance faults is because of the physics of the situation in the control loop, not necessarily because of the design of the FDIR. We need to go into this in more detail, I think. I don't think we're going to be able to do this from this report. Anyway, right, is this an accurate understanding of the issue, or how would you characterize the failures? Again, it might not be due to failures. And actions to mitigate. Were there any similarities to the OFT1 failures discussed at this time? With current hindsight and not trying to point any fingers, there we go, that's good. Do you think the OFT2 failures could have been from higher than expected thruster temperatures similar to the crew flight test? After the first OFT2 launch attempt, when the team discovered oxidizer valve issues, did the team discuss or expand the review of oxidizer compatibility with other components outside the valves? Was this a missed opportunity to find oxidizer compatibility issues? Did the fault tree change from orbital flight test to... Did the fault tree from orbital flight test and... Did the fault tree change from OFT, and was the RCC approach different? Was there new data presented or discussed that wasn't considered during OFT1? Was there any discussion of integrated doghouse testing after this mission? In regard to OFT2 in-flight anomaly, the thruster S1A1 exceeded qual thermal limits, blankety-blank thermal environment, but did not use propellants in their testing. Don't understand what that means. Do you remember any specific scenarios from this test? Was this documented as a TAO exception at the time? So I think this is test as you operate. Test as you operate. TAO. Let's have a look. TAYO. There you go. Test as you operate. Look at that. I am getting better at remembering these. There we go. For the service module reaction control system in-flight anomaly closures, the ERB, Engineering Review Board, charts had a statement under blankety blank was considered, but since the flow is blankety blank to flow resistance would be minimal, was there any analysis from Aerojet Rocketdyne or Boeing that was used to make this statement? Crew flight test mission 5th of June to the 6th of September. For crew flight test, it seems that poppet swell was discovered from the White Sands test facility testing conducted and has become the leading candidate for the root cause. It's ridiculous. If you're talking about root causes, it will subconsciously focus your mind on one topic, when actually there's many other things going on, maybe even more important or dominant than this particular one. Please resist talking and thinking about things through the lens of root cause, because you will miss things, you will ignore things. In fact, I'll give you an example. So this last last week, end of last week. I went on an adventure with my coaching group that I'm a part of. We went to Poland and we took part in some weapons training, firearms training. And as part of that activity, we did some close quarters combat in a close quarters battle, CQB training inside a kill house with live ammunition. And as part of that training, we were essentially assaulting rooms, moving between rooms and clearing rooms as a pair or four. And when I did the individual room clearance task, one of the things I made a mistake was essentially clearing the entrance to the room, moving into the room, and then staying in the doorway while I cleared the rest of the room out. And my teacher, my coach, fantastic set of guys, basically said, look, if you stay in the doorway, you're going to get shot, you're going to get killed. Because everybody in that room, when they hear the helicopters coming in or the explosions outside, they know that someone's going to come through that door very soon, and they're going to be focused on that door with their life depends on it. They'll have their weapons trained on it and everything. And so as soon as you go through that door, you need to move through that entrance as quickly as possible and out to the sides against the walls. Because humans, they are focused on a particular target. And it takes a lot, especially when they're so focused, their life depends on it. They're scared, they're anxious, they're anticipating, mortal combat. They'll be focusing on the entrance. And if you move through the entrance as quick as possible and away from it as quick as possible, they will essentially be blind to you. It is a standard human factors issue with fixation. And so talking about things from a root cause perspective, you're essentially focusing on that open door, and you've got the boys in black coming through that doorway as quickly as possible, and you're just going to miss it. You're blind to it. So please, let's move on from talking about root causes. Anyway, elevated temperatures beyond qual levels created. An environment where the nitrogen tetroxide bubble boiling was occurring, and the high temperatures also created elevated back pressure behind the poppet seat and softened the Teflon as well. Is this an accurate understanding of the issue, or how would you characterize the failures? Looking at the peak temperatures seen in crew flight test, it seems that they are somewhat higher than orbital flight test 2 and cooler than orbital flight test 1. What do you think caused the temperatures to be elevated in crew flight test? Crew flight test had issues and some new modified steps to finish propellant loading. Is there any chance or any way that changes to propellant loading procedures subjected the poppet seals to a new environment? That is a very interesting question. That's the first time I've seen this mentioned in the report. So this, if we were doing a cast analysis, we would, at this point now, we would add another part to our master control structure model to explore the sort of operational control structure involved in loading propellants into the spacecraft. And again, you might say also there is a a ground test part of the control structure, which will look at how do they load propellants into the craft and what tests do they do to make sure that there aren't any issues before, during, and after loading. So that's very interesting. Okay, high pressure differential, higher levels of vacuum, more time at pressure, and opportunity for NTO to get behind the seat. Okay, summary. Are there any other issues that you think are important to understand the similarities, differences between these three missions as they relate to RCS thruster failures? What didn't we ask you that you think we should have? That is a fantastic question. I always ask that when I'm working with my clients and trying to get clarity on where they are, where they want to get to, and are there any questions that you think should have asked that I haven't? What are they? And it's an open question. What didn't we ask you that you think we should have? Are there any other issues that you think are important? I would suggest not saying are there any. I would suggest saying, wherever my pen's gone, there it is. What other issues do you think are important to understand the similarities, differences between these missions? And I wouldn't say as they relate to RCS failures. I would wait for this question to be answered first and then focus on the RCS thruster issues. And I wouldn't refer to them as failures. It's kind of difficult because whether they are a failure or not depends on the context from which you view the problem. So looking at it from a very broad lay perspective, it's the thruster failures. It's the thrusters that have failed. Whereas when you dig into the control structure, you start to see, well, there are many reasons why that, symptom has been observed, and they're not necessarily due to failures of the thrusters. It could be due to many different parts of the control structures, all conspiring to this thing you can see and are labeling as a failure. Do you think the process for analysing the failure, determining likely root cause, and working toward a resolution is better today? No, I do not. I think that there's an opportunity here to use the stamp-based methods to supercharge this. Not just for this program either, the whole shooting match. Maybe specifically, do you think the failure investigation process was thorough? I think what they did was thorough, but it was thoroughness on part of the big picture, not the whole thing. It's like washing your car. They've washed the outside of the car and the wheels, but they've not opened the car and looked in the boot to find, some leftover sandwiches from last week. As a silly analogy. The process is not good enough because it's based around failures and root cause. Is there a possibility the team latched onto the first most credible cause? Yes, absolutely. But again, that's a combination of standard human factors and the tools they're using for investigations. Do you think our current process will get to an accurate root cause and lead to testing and analysis that will prevent failures in future missions? Again, what does it mean, get to an accurate root cause? What does that actually mean? You need STPA. You need STPA. Right, okay, so that's done. So we've done Appendix B. Let's just zoom out and sort out Appendix B. Where is it? There it is. So we've done Appendix A, Appendix B. No. There we go, right. Why isn't it working? Come on. Right then, so done Appendix B, interviews, interview questions. Right, Appendix C now. So Appendix C, as you can see, is relevant links. So I think that's probably a reference list or a links list. There's SDRT, document presentation, review and notes. Yeah, so that's completely blankety blank. Appendix C is nothing in there for us to learn. Appendix D then, let's have a look at Appendix D. So this is the reference to the SSP 30599 revision Foxtrot safety review process. So there's a number of phases, three phases, pardon me, with some timing, and then a general safety effort. So phase 1, we've got preliminary design review, develop safety analysis assessment report to reflect the preliminary design, define the hazards, define the hazard causes, use STPA at this stage, you'll do so much better. Evaluate action for eliminating, reducing or controlling hazards, identify approach for safety verification, prepare a description of ground assembly maintenance and normal operations, determine compliance with SSP 521 and 51700 requirements. Don't know what they are, we could probably look at it. Assess preliminary design against those standards or those requirements. Evaluate preliminary hazard controls and safety verification methods. Identify interface hazards and requirement inconsistencies. I mean, this, to me, this is really superficial. This is like really superficial. Maybe the document itself contains more detail, but that's very superficial, that. Critical design review. Refine and expand the safety analysis assessment report. Evaluate interfaces and mission for ground operations, procedures, plans, and timeline. Update hazard descriptions, causes and controls. Finalize test plans, analysis procedures, or inspections for safety verification. Finalize description of ground assembly, maintenance, and nominal scenarios. Determine compliance with SSP 521 and 51700 requirements. Assess the final design. Identify potential non-compliances. Concur on specific hazard controls and safety verification methods. Yeah, I don't think that's enough. That's really superficial. Anyway, prior to processing end items for launch, complete safety analysis. I'm not being funny, but it's a bit late to be completing safety analysis by this point. It should be literally, has the design met the requirements, yes or no? Not more analysis, because the output of the analysis should be the requirements. Unless, of course, the analysis report in this context is supposed to capture fulfillment of requirements. Maybe that's what it means. For the safety review panel, complete all significant safety verification tests, analyses and or inspections. Open standard safety verification items are documented on the SVTL. Submittal of the flight safety certificate to the safety review panel. Foreground submittal of the GSRP safety certification letter to Kennedy Space Center operations. Approval of final safety assessment, resolve non-compliances, identify and resolve open safety items, certificate of ground safety compliance. You see, that's really interesting because I would have thought, and I'm just thinking here, I would have thought that we've got a control structure that focuses on the design of the product, service, or system, the spacecraft. But we've also got others that should be doing safety assessments for the integration of that spacecraft into the ground environment ready for launch, and then also when it's in space. So the interactions with the ground control team, and in the case of the rendezvous with the International Space Station, how is the safety case dealt with for both of those? So again, if this is what the process, if this is the level of detail the process is written at, and we've not checked it, but if it is, this is very superficial, and you're going to need really, really experienced safety engineers that have been doing this many, many years to make sure nothing gets dropped down the cracks. But again, I can appreciate this is probably just a copy and paste from above. Post phase 3 activities. Verification complete, close items, assess real-time changes, support ISS, safety, flight readiness review, endorsement. Okay, that's great, but what about, where's my pen again? Why is it over there? What about incident response? I can't write on here. Incident response and recovery. And investigation. Support. I can't write. There we go. Support. Because this kind of touches on the system life cycle. And also, before this point, I should also add on this. What about concept? Concept development. Why is that not considered in this list? Because by the time you've got a preliminary design, your design team might have designed a dangerous system already. So we really should be doing safety earlier. Now, again, if you're doing traditional safety, fault trees and FMEA and all that kind of stuff, functional hazard assessment, you can't really apply those before you've got a concept. You might be able to do some basic stuff, but not anything that's going to have a huge impact. Whereas if you use STPA, or especially STPA, Systems Theoretic Early Concept Analysis, you could, identify a lot of important requirements and architectural constraints and functional and non-functional requirements in the design stage, in the concept stage, should I say, before you even get to preliminary design. And then part of preliminary design is to make sure that those earlier requirements, constraints you define during concept are actually fulfilled by the preliminary design. So that's Appendix D done, everybody. Look at this, we're getting close, Look at that. We've got like 4 appendices to go, and then we're done. Let's just have a break and check the chat, see if people are still with me. Please send me a comment if you're still watching. Where are you watching from? There we go. Make sure I'm unmuted. So we're now at 3 hours, 27 minutes and 40 seconds. How fantastic is that? It is so hot in my office. So let's do the final push then. Is everyone ready? Here we go. Right, Appendix E timeline then. So I'll get my yellow pen out because I like to mark things with yellow when we're talking about time. So this is the raw timeline data. So these are just the dates. So we've got Boeing, SAAs, contracts, Boeing milestones, dates signed. So there's the PDRs. That was interesting, wasn't it? Another PDR. TDR, I don't know what it is. Propulsion CDR. CBR. Safety review. Delta CDR. Delta CDR. Don't know what an SCDR is, can't remember. Yeah, then there's a hot fire abort test. Another hot fire. Yeah. So then this bit. Right, okay. So there's a timeline diagram, and this is where the data comes from. So if I just zoom out, yeah, these timelines. The source for these timelines is that list in the appendix we've just been looking at. There is another timeline as well somewhere. Yeah, this one. So this is another timeline. So that appendix is basically all of this data on a nice timeline. So we've already gone through that, to be honest. We've already read it. Oh, pardon me. So there's no need to... Oh, actually, look. There we go. So that's important information. Gold is NASA, blue is Boeing, red is SpaceX. Oh, so SpaceX is mentioned in there. That's interesting. So they were doing loads of stuff then. Wow. So they did loads of flights. Crew 1, Crew 2, 3, 4, 5, 6, 7, 8. Wow, they were proper going for it. Okay, interesting. Right, Appendix F then. Or Appendix G, should I say. Is that right? It says Appendix F there, but it's not. Yeah, okay, right. Commercial crew, transportation capabilities, contracts. Excerpt from the request for proposal, public domain. Government insight. Introduction. So government is a candidate for inclusion in the control structure. Government insight is also a potential candidate. Provides NASA commercial crew program and ISS program management, an understanding of the contractor's activities to assess the status, critical paths and risks associated with successfully completing contract requirements, achieving final certification and successfully completing post-certification missions. Government insight will include insight, quality assurance function, and a joint test team. Participation as defined below. Government insight is defined as gaining an understanding of the contractor's activities, so that's some kind of feedback, and data through an effective working relationship, inspections, interactions without approval or disapproval authority. That's important there. And provides information for the eventual certification approval. This clause describes the intended primary working level interface between the contractor and the government during execution of this contract. It is intended to facilitate an exchange of information adequate for nominal activities. The government reserves the right to implement remedies for non-conforming services or work. These remedies are described in this clause: inspection of services and research and development work, fixed price deviation. I already spoke about how fixed price control actions for fixed price work can cause significant problems in major programs, especially with program management and project managers who don't understand the engineering activities, the detail, the challenges, especially in the safety process. They underbid things systematically, either because they're incompetent or they just don't care, or they're doing it on a purpose so they can try and make more money out of it later on. I've seen that so many times. It destroys trust between the client and the provider, and it destroys trust amongst the employees and contractors working in there. Okay, right, let's keep going. So the contractor shall ensure that the government has insight into all subcontractors and suppliers performing any or supporting any critical work associated with this contract. So critical work. Details of the contractor's approach to insight to accomplish items A1, A2, A3. 1, 2, 3. 1, 2, 3. So this one, and this one shall be implemented in accordance with the DRD Insight Implementation Plan. Notification: the contractor shall notify the commercial crew program designee of technical meetings, control boards, reviews, tests, and areas identified for government quality assurance associated with certification and post-certification mission activities in the mutually agreed timeframe to permit meaningful government participation through the entire event in accordance with the Insight Over Implementation Plan. Access. So A, B, C. Right, let me just draw a line. So we've got introduction, notification, and then we've got access. And then we've got joint test team activities, government quality assurance functions, result of insight, contractor responsibility. So access. The contractor shall provide the government and its support services contractors under suitable protective conditions access to all contractor activities associated with certification and post-certification mission activities under this contract. Activities include but are not limited to CCT Plan 1100, Crew Transportation Plan Appendix C, Insight Areas. The contractor shall provide the government and its support services contractor access to all data used in the performance of this contract, all data, including but not limited to data associated with areas of insight identified in the plan, Appendix C, and supporting data information and administrative and management information with the exception of financial information and any other information not used in performance of the contract and any other information not used in the performance of the contract related to the crew transportation system design, production and operations to include technical data, supporting data, information and administrative and management information with the exception of financial information. I mean, that sounds to me like it's pretty clear that they want to see everything except financial information, which you know is understandable. At a minimum, access to data is the ability for government and its support services, contractor personnel, both remotely and on-site at the contractor's facilities, to locate and review all data as defined in 4 directly below in a usable and readable format. The government may use the data to which it has access under this provision solely for the purposes specified in paragraph A1. Okay. The contractor shall provide office space co-located on site, badging, furniture, telephones, and use of easily accessible fax, data lines, and copy machines for full-time and temporary government personnel and its support services contractor for performing insight activities in accordance with the RD Insight Implementation Plan. Joint test team activities will be contractor-led, reference the plan, and shall include activity and steady-state government participation. Both on-site and remotely, the contractor shall accommodate government personnel who will provide embedded insight during the activities identified in D2. Government JTT joint test team personnel members will not provide direction to contractor personnel on design changes or procedures or any other aspect of CCS development, production, or operation. That is very interesting. I think we've found a reason why this accident occurred. Government JTT members provide insight only and will not approve or disapprove any aspect of the, this is disprove. Hang on, let me just move this bar out of the way. Will not disprove any aspect of the contractor's CTS design or performance of the contract. Any actions taken by the contractor in response to any direction given by any person other than the contracting officer shall be at the contractor's risk. The JTT will provide a formal, unambiguous programmatic structure for government operationally focused input to the contractor. I wonder if that was done, what the reference is. Because so far, these statements here, this explains a lot about the way the control structure behaved. Because if they're, sorry, not this bit here. If it's just a test team, I totally get that. But the function of providing direction or at least advice or support is a necessary function, but this forbids it. And if you have any individuals involved that are very, to the line of the contract, work to the rule, that's going to set up some serious difficulties and issues with trust and support amongst the team members. This is, this is interesting. Right, let's keep going. Let's go. There we go. So in addition, the government lead on the JTT will provide integrated consolidated operations insight to the CCP. By its structure, the JTT will prevent unintended informal government inputs to the contractor. By its structure. To the maximum extent possible, the JTT will work together and strive to resolve operational issues at the lowest level. I think that's fundamentally flawed. I think it's too constraining. It'll breed mistrust amongst the stakeholders. We'll focus on qualitative assessments of crew operational interfaces. So this is crew operational interfaces with the vehicle and human-in-the-loop assessments of operational suitability. These assessments will include, but are not limited to, vehicle handling qualities, situational awareness, workload and operational complexity, usability, cockpit layout, displays and controls, and flight crew suits. In addition, the insight will occur through participation during the planning and build-up phase of ground testing, e.g. simulator training, evaluations, mock-up demonstrations, etc. During flight tests, during the post-test flight evaluation process, insight gained through integrated operations assessments will ultimately feed into NASA's verification approval decisions before test flight and validation approval decisions post-test flight. Okay, government quality assurance functions, GQA functions. The government will perform the following quality assurance functions: product examination, process witnessing, record review, surveillance, and audit. Government quality assurance functions will be performed for all safety critical items, processes, products identified by a risk. But there you go, there's the problem. By a risk-based analysis. An RBA is an iterative analysis based on comprehensive understanding of the design. Well, clearly that's not possible. Of the design, development, testing, critical manufacturing, assembly processes, and operations used to identify areas of risk. This is not possible to achieve with this, where is it? The GTT Insight activities, or where is it? Or this bit about all data. If all the data is not provided, or access is difficult, whatever, limited, then we're not going to be able to create a comprehensive understanding of the design, development, testing, critical manufacturing, assembly processes, and operations used to identify areas of risk. On top of that, if you've got the joint test team, joint test team activities where they're not providing any direction or anything like that, then again you can't do this. What this is saying you need to do, if that's what the contract says, you're not going to be able to do it. Not without lots of arguments and stress. The contractors shall support the RBA by providing technical expertise as required. The definition of safety critical is found in that requirement document and this process. So that's an interface requirements document, and this is a requirements document as well. Result of insight. Insight should result in an effect. Insight should result in an effective working relationship. Should it? Does it? No, in my experience over the years, it's always been challenging. Always, without exception. And the contractor, leading to NASA certification of the contractor's crewed commercial transportation system. Should insight and/or JTT participation identify non-compliance with the requirements, the terms and conditions of the contract, or a difference in interpretation of test results, or a disagreement with the contractor's technical approach. The Government Insight team will evaluate the issue through the appropriate CCP boards. Through an effective functioning relationship, the government and contractor should strive to resolve issues at the lowest working level and minimize issues elevated to program boards. See, that's interesting. Minimize issues elevated to program boards. So if that's what we're asking people to do, then we shouldn't be surprised when things get dropped off or not escalated. Because we're asking them not to do that. They should strive to do it, but are they resourced to do it? It's a nice intention in principle, but the reality of a real complex program such as this, it's nice in principle, but that's not the reality. That's just my experience. People, when senior leadership are saying, well, the contract says you need to resolve the issues at the lowest working level and minimize issues elevated to program boards. If those at the bottom have issues and they're saying, hey, we need resources, we need support, and all they're getting from above is, well, you need to deal with it, you need to deal with it. People are going to stop reporting upwards. I'm not saying that's what's happened in this situation, but that's what this implies. This is basically driving those people to try and solve problems themselves, and driving themselves off a cliff. That's what this is suggesting. Program boards will disposition recommendations in a timely manner and provide oversight resolution if necessary. See this? Provide oversight resolution if necessary. That's not the same thing. You see, this is talking about insight. This bit you can see there, insight. But this is talking about oversight. They're two distinct things. They're not the same. They've got different functions. Resulting board decisions, direction. So these are control actions, everybody. Board decisions and direction will be transmitted to the contractor through the contracting officer. So they are very important. If this disposition results in a requirement change, the change clause would take effect. If the contractor and contracting officer disagree on whether the board disposition provided is within the requirements of the contract, the dispute clause is applicable. So I think that they are key stakeholders in our control structure model. So we've got contractor, we've got government, we've got contracting officer. There we go. Right. Right. The data generated as a result of government insight may be used, modified, reproduced, released, performed, displayed, or disclosed within the government and its support service contracts as under suitable protected conditions. The government may not, without written permission of the contractor, release or disclose the data outside of the government, except as otherwise required by law, use the technical data for manufacture, or authorize the technical data to be used by a party outside the government. Contractor responsibility. Notwithstanding the insight set forth in this clause, the contractor assumes full performance responsibility as set forth in this contract. The government's insight or JTT participation under this clause shall not be construed as authorization, endorsement, or approval of milestone certification or final acceptance or rejection of the post-certification mission success. Okay. So that's the end of that. So that is the commercial crew program, commercial crew transportation capabilities contracts about government insight. So I imagine there's probably a section H16 that talks about government oversight. But that contract, if you were to do an activity, take that contract, review it from end to end, build the control structure from the content of it, or for one of each section and then see what comes out. I'm confident you'll find holes and weaknesses in it. I mean, even just this section, this bit about not providing direction, will not approve or disprove any aspect. I understand why that's there, but some of those things can actually undermine or harm the safety-related decision-making and sharing of information. And this bit here about risk-based analysis, you know, like I've said many times before, when we're talking about complex systems, we need to get away from trying to put a number or between a number of between 1 and 5, or 10 to the minus 9 per flight hour, or whatever it is. We need to try and avoid getting tied up with risk-based analysis, especially when it's program risk and not safety risk, or letting the two, letting program risk decisions overwrite issues with safety and safety risk. Okay, the last part then. So Appendix H, or hotel. Oops. Oh, it's not in there. Look, we can't mark it off anyway. So Appendix H is the Boeing Enterprise Root Cause Corrective Action Summary, and it's obviously blankety blanked out. I understand why that is, but I'm sure that contains a lot of interesting information in it. Appendix I is the Senior Review Panel response to the investigation team report. This was December 2025. So this is just basically saying that the Senior Review Panel has participated in the program investigation team and helped them, and it all went really well and they endorsed it. And that's it. That is the end of our journey with 31 live streams and about 70 odd hours of review content over the last number of months. So what I'm going to do is I'm going to pull stumps there. Let's just go down here, make sure we've got everything. Yes, we've got that. There we go. That is phenomenal. And my monitor's going to turn off because they've been on all day. I've been busy all day. There we go. Right. So that's it. That's the end of the report. That's the end of the Boeing Starliner pit report. Please click the link or use the QR code there to visit my homepage and join the waiting list for the free workshop. So stick your name and address in there, press join the wait list. And once I've finished, thinking about all this stuff, I'm going to put some slides together, and then I'll send an email out and we'll get together and we will talk about this and talk about and answer any questions that you have. So yeah, thank you for sticking with me through this. It has been a long journey. I've certainly learned a lot trying to do live streams and all of that good stuff. And also thinking about through the content in this investigation report and trying to manage my own expectations. Because I kind of expected something different to what it was, and was pleasantly surprised in some areas and then rather disappointed in other areas. And again, that's not a judgment of the people involved. They're trying to do their jobs. In the case of the pit team, I understand from the investigation report, they were essentially trying to do this investigation alongside their day job in very challenging conditions. So I completely appreciate the level of effort that's gone into this. And so if I do sound overly critical, it's not critical of any individuals at all. It's just, what can we learn? How can we learn better? How can we learn faster? And ultimately, the main recommendation is, please use stamp-based STPA hazard analysis and CAST accident analysis, because you could find so much more. And I'm hoping actually today, the session today, where we were working through the, if I just zoom out again and show you, where we started working through and building a more technical control structure. So this aspect here. So we were talking about, the physical process and then the different layers in the structure and what the potential control actions and feedback might be. So I hope that was helpful. Join the waiting list and I will be in touch and we'll get together and have a fantastic time. So thank you very much for watching and I'll see you soon. Take care. Bye-bye.